Hello, wonderful people of the internet. Welcome back to another episode of Leos Lab. So today we're actually going to start with algorithm archive work, finishing up, rereading the chapter on the Metropolis algorithm that we were looking at yesterday. And then once we get that out of the way, hopefully we'll do some galaxy simulations. If I'm totally honest, I was reading some papers this morning and still not entirely sure what we need to do for the last step of the galaxy simulator as we get there. So there might be a stage. And also, I've got a bit of a headache right now. I don't exactly know why. There might be a stage later today where we might do something that might not be tech related. I might put a game on stream or something like that. I'm not really sure. It depends on how I'm feeling. But as I said before, I'm really trying to get that stream stamina up, which means I'm really going to try to make sure I do from 2 to 6 today. So that's going to be my stream schedule for now. I'm hoping by the end of this month or whatever, I'm able to put, about 40 hours a week into streaming, which means basically 6 hours a day. Could be more on individual days or something like that, but that's kind of what I'm trying to figure out how to do. Mick M. Levi, thank you so much for coming in. How are you? I hope you're having a great afternoon. Also, I just wanted to, before getting... Gosh, I'm not able to speak at all today, and I'm so sorry. Before going any further, I want to mention one thing. And that is that we had this huge discussion yesterday about I don't know how to put it, but it was what it means to do a simulation. And the ultimate question was asked, why would you want to do a simulation if you don't care about the physical accuracy of that simulation? I just want to finish that discussion because it finished really messily yesterday, and I wasn't happy with how it finished. So let me open up one more time, and let me see if I can describe my mentality here a bit more. So move that over there. What? Oh, I see what happened. Perfect. Okay. Right. So here was a discussion point. The question was, what is the point in doing a simulation if you don't care about accuracy? Right. That was the question. And again, I'm not going to spend more than 10 minutes on this. We had literally a 30-minute long conversation yesterday. I just want to bring this up, say my bit about it, and then move on, right? So yesterday I made the point that the simulator that we're doing will be a galaxy simulator, and that I don't particularly care about the physical accuracy of the galaxy simulator. But that came off as me not caring about the physics at all, which is also kind of true. I'm very jaded because I did a PhD in physics, and I did all this stuff in physics when I don't really care that much about physics. So I might have said something along the lines of, I don't care about the physics at all here. I'm interested in this, right? And for the record, what I said was, I don't care about the physics because I'm really interested in the N-body simulator. That's kind of what I want to do with this project, right? Now, that was interpreted as, I don't really care about the physics at all. It means that I'm just going to do any willy-nilly simulation, and if it doesn't match physics, if it doesn't match physics, fine. Happy Little Rat, hey, I'm here to help. Break the 10-minute limit. That's fair. I promise I'm not going to ramble much beyond that. So, I just want to say something to be very clear. One, the simulation that we are running is going to be physically accurate. We're using a model that's maybe 5 years old, but it's going to be as physically accurate as those models get. The point for the simulation is not necessarily to make it so, we have the most physically accurate galaxy simulator. The point is to make sure that we can do fast N-body calculations, which are useful for a variety of different fields. But none of that is what I want to talk about right now. The question is the following. What is the point in doing a simulation if you don't care about accuracy? Well, here's the thing. If we're talking about large-scale physics simulations, there are 10 different ways to do a physics simulator, and oftentimes you have to build all of these different simulation methods together to make the most accurate model, right? There is a point in just picking one of those types of simulators, here an N-body simulator, but potentially some other simulator as well, and improving just that one aspect, right? So what we're looking for is a way to, do research in a field without knowing deeply exactly, what the, full ramifications of the simulations are, right? So I need to care about dark matter, but do I need to care about dark energy? Do I need to care about Minkowski space? All of this kind of stuff? Probably not for this simulation, right? And I think it's really important to keep in mind that, even though I don't have the deepest understanding of all of this physics, the point of the simulation is to improve individual components of the simulation, not to, create a broader. I'm not trying to create a new theory of physics. I'm not trying to solve anything there. That's just what I wanted to say. What we need to do is attack a very small aspect of something, improve that as best we can, and then let other people who are better at the broader scope of physics, who are better at incorporating this with other models, to take what we've done and run with it, right? Our point is just to hone in on one particular part and make that good. And that's kind of what I wanted to say. That's all. That's just what I want to say. I don't want to dig into it too much deeper. It's still not particularly clear, but I think it's clearer saying that than what I said yesterday. I randomly wrote N-body simulation last Saturday. I realized you were doing the same stuff. Probably picked the idea from you. Oh yeah, N-body sims are sometimes remarkably easy and sometimes remarkably complicated depending on how you do them. Didn't care about accuracy either. It was just a fun, simple thing to relax with. Right, exactly that. The N-body simulator that we're doing right now is particularly useful for some of the computer graphics stuff that we're working on in the near future. Anyway, the point is, there was someone who mentioned in chat that, if you're looking for the fastest simulator, why not just printf Galaxy Sim? Why? And I'm like, dude, just obviously we're doing a real physics simulation here. It's just it's not the most accurate one. It's accurate enough. Also, I think fun is a huge aspect. I mean, one simple improvement can spark new ideas and develop things. Right. Optimizing N-body is a heck of a complex and deep problem. Oh yeah, definitely. 100%. Which is why I feel confident that if we focus a bit on it, we can actually do some really big improvements here. Miabdi, hey, how are you? Right. Also, one thing that Mick Levi, I don't know what I should call you, Mickey Mouse Levi, Mick M Levi. Anyway, what Levi said is, I think, true. What I'm trying to do is create an open research company that engages people from everywhere, right? And part of that is the fun aspect of it. Part of that is doing something that is, people probably wouldn't have thought of before, that sparks interest in the topic that they wouldn't have had before, right? That's what we're doing. And if we can publish, that's what we're looking for, something that's publishable, but also interesting enough to grab general audiences. So I don't care so much about the novelty of the publication. I want to make sure we get a publication, but I don't care about is this going to be the most highly cited paper? Right now we're looking at just finding a way to engage people with academic literature. That's where we're at. And so even if the paper's not the best paper ever, even if it's probably not even going to be cited that much, just getting to that boundary of human knowledge is where I want to go. And just showing people that this can be fun is also something that I think is really important here. Making a working N-body simulation is probably among the simplest physics possible. Yeah, it's really easy. Making it efficient is really difficult. And so the reason I liked this problem is because it's a super large N-body simulator, but that's all it is. The trick is making it fast, making it possible on a GTX 970 GPU, but I've got better GPUs available if I need. This type of thing, Okay, so as you can see from the title, we're actually going to tackle some algorithm archive work first before going into the N-body simulator. So we're going to do that in maybe an hour or so. So let's go to github.com. And where are we? Something like this. And I'm going to pull up the latest pull request for the next chapter, which will be on the Metropolis algorithm, right? So let's go here, files changed. So some of you guys may not have been here yesterday, but essentially we ended the stream yesterday by going through the chapter on the Metropolis algorithm, which also implemented another chapter on probability density functions. So yesterday we went through the section on probability density functions. Wow, I can't speak. Last week we went through the chapter on Metropolis. There have been some updates since then, so we're going to go through the Metropolis algorithm again, and then we're going to have to go through the probability density function one more time, and that's kind of where we're at. What do you think about gamification of, say, an N-body simulator? So that's actually an interesting question, and this actually brings up another good point, which I think I'll ramble about just before getting into the chapter. And I'm just going to write gamification, but in general, what I mean is how make things interesting. That's the question. A long time ago, I thought about creating a Barnes Hut game that was basically, explaining how you could weave through the galaxy, you get a spaceship, and it's just kind of moving through the galaxy, and based on how you see the world, how you change your parameters of the simulation, you can like arrive to different planets at a different way. So basically, you're modulating not only the spaceship, but you're also modulating like space itself and how you perceive space and stuff like that. I thought this would be kind of cool as a game, as like a quick concept or as like a demo. And I think actually probably doing a little demo like that could be super helpful, like really useful for a lot of people to understand kind of intuitively what's going on. Hey Gibbous, how are you? Things are great. How was the crew showing yesterday, the Cinderella theater stuff? I hope it went well. So I thought about that. I thought about doing a game here. I don't have the skills here. I know Happy Little Rat, you probably do. It's probably pretty easy for you. Oh, it's today. Somehow I thought it was yesterday. Okay, good luck with it. Yesterday I said it was tomorrow. Completely misunderstood that then. For some reason I don't know what I thought. But yeah, okay. Good luck with it today then. For some reason I thought it was yesterday. I guess just because it was on my mind, I just thought, oh, it must have happened. Error 2000. Refresh the stream maybe? I don't know. If anybody else is having trouble with stream, let me know. Maybe refresh. Anyway, so if you guys want to see like kind of research related games, I'd be interested in doing that. Ultimately, like, you know, you guys know I make YouTube videos, I do Twitch streams. My whole purpose is just to get people to engage with research, no matter how we do that, whether that be interesting YouTube videos, that be game demos, whether that be like anything else. I don't really care. The point is I want people to engage with something that they hadn't engaged with before and enjoy that engagement. So if you guys have ideas of things that you might want to do, let me know. I don't have any funding now, but I might be able to put some development time for it. I don't know. This is kind of where I'm at. I'd love to get to a point where like I actually have funding that I can give to people to do projects like this. But I just don't have that right now. I'm barely able to keep myself afloat. I mean, obviously, you know, it's me and my wife together keeping ourselves afloat, but you know, I would like to build this into a business that I could do more with. And I've been trying to think of different business models and stuff. Part of what I do in the morning is kind of brainstorm different ideas of how to get this to work and stuff like that. I got some vague ideas. Yeah, so there's some other stuff that I was thinking about as well. Like, for example, the ASCII art generator that we're working on. A long time ago, I wanted to make an ASCII video game called Specterm, and I'm like, maybe I should just make that game. You know, if we have an easy ASCII art generator, maybe that's what we do. Anyway, okay. So what I'm going to do now is I'm actually going to do a review of the Metropolis algorithm implementation for the algorithm archive, and then we're going to hop into the Galaxy Simulator. I'm hoping by the end of the day, which will be at 6 o'clock p.m. my time, which is in about 3 hours and 45 minutes, we'll have like something working. I don't know what, but we'll have something working. We can go a bunch of different ways with it, but we'll see. That's actually funny. I too have been wanting to write a tool that converts images and videos to ASCII. Right. So actually all of this, you have gotten better with about time management. I'm trying to get better about time management, but you know, like I'm not that great. I'm hoping at the end of this month, and I said this before, I'm hoping at the end of this month, I can put like a majority of my workday on Twitch, not all of it, but a majority of it. Like a lot of like the reading papers and kind of like thinking and figuring things out still have to happen off stream. But yeah, I did get my flu shot yesterday. Oh yeah, how was that? I mean, I assume it wasn't as like, not painful, but I assume there weren't as many issues as there are with like COVID vaccines and stuff. I gotta be honest, I don't normally get a flu shot. I know I should. Like every year I'm like, I should definitely get a flu shot, but I don't. And my logic is that I barely never go outside. And I, for that reason, don't interact with enough people to even spread the virus, even if I do get sick, you know? But I know I should get flu shots. I'm always lazy about it. Okay, so we're gonna go into CD projects, algorithm archive here, Alice here, get branch. Let's pull down the latest changes. I don't get a flu shot. I also don't get sick much. Yeah, I mean, to be fair, like I do. It's kind of a bad argument to say, like, that's the same argument I always do. Is like, oh, I don't get sick that much. But, you know, like, I get it. Like, with the whole COVID thing, like, it's become more apparent that I should be more cautious about getting other people sick. So even if I don't feel sick, you know, I could potentially get someone who could really, really, like, greatly be negatively affected by this. At least flu shots slow down the spread. Right. Okay, so here's what we're going to do. We're going to go here and go to conversation and grab the latest changes. Oh my gosh, come on. Scroll down. And then we're going to take a look at the Metropolis algorithm. Okay, so command line instructions, and we should just be able to run a git pull, I believe. All right, let's give this guy a go. I think I can just do this. Got my COVID booster. Man, okay, here's the thing. I have been the moment we could get a COVID shot, I went out and got one. So this is way back in March. But then I moved to Okinawa, and now I'm in Barcelona, and I'm not sure if I can get a COVID booster. Like, I don't know how to convince people that, like, I actually have my vaccines, you know? Let's see. COVID shots don't really affect it spreading. Could you give us a quick recap on what this problem algorithm is? Actually, yeah, okay, let's start there. So what we're working on right now is the Arcane Algorithm Archive. It's a book on algorithms. So for example, here's the Barnsley Fern. And you know, you can scroll down to like a code snippet or something, which is apparently way down here. And you can switch between all of the different code blocks. And so the idea here is that we're trying to teach algorithms in a way that is intuitive, but also like language agnostic in a way. Like we could have chosen to just use like pseudocode, but having it available in a bunch of different languages gives you a more, like it really does give you a feel of how to actually implement this in code, whereas pseudocode usually does not. And so the algorithm archive, in some sense, is like numerical recipes in that it's supposed to be like a book on algorithms, but it's also, in another sense, kind of like a Rosetta code in that you have a bunch of code snippets available. And so right now we are reviewing a new chapter submitted on the Metropolis algorithm, which we're actually just going to read through the chapter now. So as an introduction, hopefully this gives you an introduction for what it is. So rather than being like, this is what the Metropolis algorithm is, I'm just going to vaguely wave and say this algorithm is kind of like a Monte Carlo approach for integrating probability density functions. That's what I'm going to say. And then hopefully the chapter gives you actually that intuition. If it doesn't, and if you have a question, then that's the perfect question to ask, and that's the perfect question for me to ask in the review. Okay, CD projects. Algorithm archive, 1 second, and then npm. One more thing before continuing. I'll get to your comment in just a second, happy little rat. If you guys don't want to just like hang out, chat while we're doing the algorithm archive reviews, I do understand. We'll get to the 4D galaxy simulation in like, I don't know, like 45 minutes or an hour, just, you know, enough time for me to go through this chapter and make sure there aren't any problems with it, right? We're trying. You can probably get some evidence. You get the first one, or they take your word for it and give you the second. Yeah, so originally, I was not planning to get the booster in Europe because I was going to... go back to the US this winter for Christmas, and then I was going to get the booster then. But unfortunately, I'm really not able to go back over Christmas due to various like visa restrictions and stuff like that. So I won't be able to, I just won't be able to check or get the booster when I go back. Okay. Okay, it's different. Let's see how this goes. All right, I'm going to read through it. I'll make the text bigger so everyone can read through it together. And we'll just go from there. Okay. If you guys have any questions, comments, concerns, ideas, anything like that as we're going through, please feel free to let me know, and I'll totally address it as soon as I see it in chat. Outside of that, we're just going to be reading through the chapter, reviewing it, making sure it makes sense, and then hopefully merging it into the algorithm archive. At some stage, I'm hoping to kind of take on more of like an editor role for the algorithm archive. I realized that just recently in that, a while ago I wanted the algorithm archive to be completely written by me, but now I do understand the utility in having other authors. Like I always have understood that utility. It's just I didn't know how to actually get it done. And so now it's like, okay, fine. Let's just do that. Let's be more of an editor, still write chapters when you need them for your specific research, but in some sense, I don't want to necessarily go through and like have, a chapter or a video on every algorithm, right? Like I don't want to have to be the one that writes that, Okay. So let's go through. Too much work. Try to distract you. I'll get back to work. All right. See you then. Have a wonderful, I guess afternoon, your time. I think you're at the same time zone I am now. Maybe off by a few hours. But anyway, have a good day. Maybe I'll see you lurking around here. Okay. So Metropolis algorithm. I feel like maybe it should be the Metropolis algorithm. Okay. I'm already literally at the title and I'm already picking it apart. All right, let's go into the chapter and let's go there. 1523. Oh, so you're an hour ahead of me. Okay, let's go down to the Metropolis algorithm and just start hacking away. It should be here. Perfect. And let's just do it. So, wait 1 second. Suggestion. Grab this line, paste, and do the. Okay, start review. All right, let's see how this goes. Monte Carlo integration, make sure that link works. Perfect. The Monte Carlo integration method uses random numbers to approximate the area of pretty much any shape we choose. The Metropolis algorithm is a slightly more advanced Monte Carlo method, which uses random numbers to approximate a probability function. Perfect. Okay, this guy should bring us down to the bottom, as it does, although it is weird. No, I think it's fine if I just click this. Yeah, okay, it brings me down to the right location if I click that. Perfect. Okay, let's just keep going. See, I'll try to remember to catch the Galaxy stuff. Yeah, the Galaxy stuff should be happening in like an hour. I'll change the stream title and everything when that happens. Okay, here we'll use the Metropolis algorithm to approximate a probability density function as described in this chapter, which is of the form this, where D is a domain of P of X, i.e. all possible values of X, for which P of X is defined. And F of X is some function that is proportional to P of X. Sure, okay, such as a frequency distribution of X. A one-dimensional example of this is the normal distribution or Gaussian distribution given by the following. Sure, okay. In practice, it's often easy for us to know f of x, but the integral in the denominator can be quite difficult to calculate, even numerically. This is especially true when the coordinates x are multidimensional, and f of x is an expensive calculation, as we'll see in the examples below. Wouldn't instead of writing this chapter, writing the chapter title itself out be clear? Wait, let me reread that. Wouldn't instead of writing this chapter, link, did I miss a link? Writing the chapter title itself would be clearer. Yeah, I think so. That's probably fair. I see this guy here. In fact, in this case, just having it be a link, I mean, we already said randomness, we already have the link right there. So it's a slightly more advanced Monte Carlo method, which uses random numbers to approximate a probability density, probability distribution. Here, we'll use the Metropolis algorithm to approximate. I think we just put a colon there and just be like, colon, this guy, and then put this sentence down below. I think that's probably the way to do it. Yeah. Let me just modify that then. Metropolis algorithm here. I think we just remove this entirely. Remove that. So suggestion. In fact, let me just do it this way. Let me go here, grab these lines there, and then do suggestion. There. What happened? Where'd it go? 1 second. I'm really bad at like any UI. Here, grab this guy. Well, actually, let's just grab this guy. There, paste it there, and just do colon. And then I want to grab this line. Yeah, sure. That'll work. Control X, and then change this there. Sure, add a review comment. I think that's fine. But yeah, personally referencing to this, I find it to be less clear than mentioning it explicitly. I agree with that. Is that fine? I believe so. Okay, we're D. So let me reread this without that sentence. So it says, which uses a random numbers to approximate. Yeah, it literally says the Metropolis algorithm is slightly more advanced. A Monte Carlo method which uses random numbers to approximate the probability density function. Then it's literally the same sentence below. Here we'll use the Metropolis algorithm to approximate a probability density function. You know, like when you're watching a YouTube video and like people are like, in this video, we're going to show you this. And then the next sentence is, this thing is exactly this thing. Like, it's just kind of like, redundancy is fine. Maybe it's useful for some people, but like, honestly, you know, it's best to cut it out if you can, in my opinion. Especially with text, because like, you know, you can just pause for a second. It's not like video where it's harder to pause or scrub through the video. I think that's fine. Now let me read this paragraph in here, where D is the domain of P of X, so that's this guy, i.e. all possible values of X for which P of X is defined. Sure. F of X is some function that is proportional to P of X, such as a frequency distribution of X. Again, what is a frequency distribution of X? Maybe I just don't know what this terminology is, but I don't know what that means. So I think I'm going to just mention that here. Again, frequency distribution is something like f of x, such as a frequency, maybe saying such as the number of, or the likelihood let's see, how do I put this? Like the likelihood of finding the likelihood of particular outcomes in a game of chance. Something like this. The problem is just the word frequencies. Like, it's used in everywhere. So it just, when people say frequency distribution, like, I naively don't think like games of chance, right? Like, I think, I don't think frequency of occurrences. I think more like signal processing. Like, you know, you do a Fourier transform. So you say frequency, I'm like, okay, so I can do an FFT here. And it's like, no, it's a completely different thing, you know? Right, okay. A one-dimensional example is the normal distribution or Gaussian distribution given by the following. Sure, in practice, it's often easy for us to know f of x, but the integral of the denominator can be quite difficult. So so the denominator here is a normalization, right? So, isn't it the normalization? I think so. Especially true when the coordinates x are multidimensional. F of x is an expensive calculation, as we shall see in the examples below. Okay, so I think explicitly state that the denominator is, 1 second. Let's see, where D, sure. It may be also an explicit mention saying that the denominator here is a normalization. Okay, let's keep going. One step at a time. Add review comment. All right, we're getting there. So, an example application. One example of a complicated probability function arises when considering a physical system of n number of particles. I think just n particles is fine. 1 second. Here, paste it there, add a O there of n particles. Add review comment. Okay. These could be atoms, molecules, or even star systems. For such systems, we can usually describe the potential energy of the system as a function of the coordinates of all particles, x. E of x is equal to E of 1, 2... Sure, okay, yeah, that's fine. Where x, y, z are the spatial coordinates of each particle I. So altogether, there are 3n coordinates making Ex a 3n dimensional function, which can be computationally intensive calculation on its own. But it doesn't end there. Wait, I'm a bit confused. Give me a second, I need to think about this. So what he's saying, or they're saying, is for such systems, we can usually describe the potential energy of the system as a function of the coordinates of all particles x. I've never seen a potential energy calculation done this way. Why? Oh, I see. So you're trying to create an n-dimensional... Okay, I see what's happening. Right, I got it. For suggestions, there is a file button with plus minus in it. Just selection selecting the lines and press that button, and it'll auto-generate the suggestion. It'll save you some time. Oh, okay, good to know. I'll take a look at that in just a second. The physicist Ludwig Boltzmann discovered that when such a system is in equilibrium at some temperature T, you can describe the probability density of the system for any set of coordinates x using the following. Sure, okay. Where Q is a normalization constant. What, is that mentioned? Okay. Sure, okay. And is equal to that. That makes sense. We can now see that the probability density function is a difficult calculation, particularly because of Q. Almost always no analytical solution exists to the integral in Q, and the numerical integration is infeasible. Unfeasible? Infeasible? Is unfeasible a word? Basically this. I didn't know that was a word. I thought it was infeasible. Let me go to Google Analytics. Maybe I'm the one that's wrong. Let me take a look at this as well. Paste this here. Oh, nice. Perfect. Okay. Let me go to, no, not analytics. I'm sorry. Google Trends. That's what I want. Then we're going to go here, and we're going to look up infeasible versus unfeasible. Able or able? Able. And then we want infeasible. Ah, I didn't know that. I'd never heard unfeasible before, but it seems like they're like basically neck and neck. Am I misspelling infeasible though? Is one British English and the other American English, and I just know one and not the other? Weird. I mean, clearly the same word. I'd never heard of unfeasible before, you know? 1 second. Fine, we'll leave it. I mean, it's fine, it's a word. I just found that weird. Okay. To see that Q is unfeasible to calculate, it just doesn't sound like a word. Imagine there are 10 particles which all exist in a 1D world restricted to a line segment. Sure. This means that the energy E of x of the system is a 10-dimensional function, as there are 10 coordinates in total. Sure, okay. Now imagine that we divide the 1D line segment into 50 different intervals, allowing each particle to take on 50 different positions. Okay, now I'm lost. Okay, I need to think. This means that the energy E of x of the system is a 10-dimensional function, as there are 10 coordinates in total. Sure. Now imagine that we divide the 1D line segment into 50 different intervals. Okay, allowing each particle to take on 50 different positions. Okay, that was confusing to me, but yeah, that basically means that it's now extending into 2D. Maybe if we consider this for 50 different time stamps, I think the intervals is confusing, but maybe considering this for like different time points or something. This is just me, I don't know. Where's the image? The image should be here. Right. Somehow the word interval is weird to me. Maybe saying that, let's see. Uh, 50 different points in time. Feel free to ignore this one. Okay. Let's keep going. Add review comment. Okay. This is equivalent to dividing the length of a football field into intervals of about 2 meters, not a resolution you'd want to watch a game in. Oh, I'm super lost. This is equivalent to dividing the length of a football field into intervals of about 2 meters, not a resolution you want to watch a game in. Even with such poor resolution, the number of different combinations of positions is 10 to the 50, a colossal number indeed. To see how large the number is, imagine that a single computation of e to the x took 1 nanosecond on a single processor, which is much faster than most energy calculations for physical systems in practice. With that speed, it would require 10 to the 41 seconds on a single processor to calculate Q, which means that even with all the processors in the world running in parallel, there could be billions or trillions of them, calculating Q would still take longer than the age of the universe by many orders of magnitude. Okay, so this is where, like, I'm personally a bit confused. So let me go here and just say, so the football field example doesn't make sense to me. So this kind of, I don't know, this is, and then I'm going to say, all of this stuff down here, this argument is nice, but so the problem is, like, you know, he's supposed to be like, wow, it's so impossible to calculate Q, but, like, is it though? I mean, what are you asking them to do? Maybe I'm misunderstanding what we're doing here. So we have 10 to the 50. So it's equivalent of dividing the total length of football field into intervals of about 2 meters. Not a resolution. Okay, let me reread this because maybe I'm not understanding what's happening here. To see that Q is infeasible to calculate, imagine there are just 10 particles which all exist in a one-dimensional world restricted to a line segment. Sure, okay. This means that the energy Ex of the system is a 10-dimensional function, as there are 10 coordinates in total. But they're restricted to a line segment. If they're restricted to a line segment, it's still 1D. I mean, okay, so you're saying these could be, okay, you're saying that this X could be anywhere on the line, fine. So you have 10 separate one-dimensional functions, which is different than a 10D function, isn't it? I mean, I don't know how the X's are combined. Okay, yeah, that's right. I don't know how they interact, so I don't know what's going on there. Let's see. Now imagine that we divide the 1D line segment into 10 different intervals. So this just means, I don't know what that means. I really don't know. I'm not understanding this at all. Okay, so we are imagining that we take the 1D segment into 50 different intervals. I don't know what this means. I don't know if this means that there are 50 possible positions for each point, which I think is probably fair. So there are 50 different positions for each point. Okay, that's what that means. Allowing each particle to take on 50 different positions. Okay, there we go. That's fine. This is equivalent to dividing the length of the football field into intervals about 2 meters. Okay, fine. Even with such poor resolution, the number of different combinations of positions is 10 raised to the 50. How did we get 10 raised to the 50 though? The possible number of positions is not 10 raised to the 50 because this is 10 separate one-dimensional. Okay, you're saying combinations of positions, but why do you need every combination of every position? Because, like, this is just the integral. Okay, okay, I'm still trying to figure this out. Give me a second. Even with such a poor resolution, the number of different combinations of positions is 10 to the 50, a colossal number indeed. To see how large the number is, imagine that a single computation of e to the x took only 1 nanosecond on a single processor, which is much faster than most energy calculations for physical systems in practice. With that speed, it would require 10 to the 41 seconds on a single processor to calculate Q, which means that even with all of the processors in the world running in parallel, calculating Q would still take longer than the age of the universe by many orders of magnitude. Thanks for the bit, Anonymous Cheer. I think this argument's fundamentally flawed because, like, what they're fundamentally asking is if you have 10 points that can be distributed along, if you have 10 individual points, I don't, okay, I'm just going to mention, I'm not really following, actually, I'm not following this argument at all. Let's go here. Where are we? We are down here. Delete. Yes. Okay, this doesn't make sense to me. Okay, let's delete that. So now I think I understand what's trying to be said here, but I don't agree with it. I don't know if I buy this. Let's see. I don't know if I buy this. are giving each of the 10 points in space 50 possible positions to exist in. Which, okay, so I don't know. So we're giving each of the 10 points in space 50 possible positions to exist in. That is certainly 10. Is it 10 to the 50 possible permutations? Sure, 10 raised to the 50 might be 10 raised to the 50 permutations. However, missed the S in exist. Oh, yes, I'll fix that. That's a spelling mistake. I can fix that later. That might be 10 to the 50th permutations. It's not clear to me why you need to use every permutation for calculating Q. I guess it's just because there are 10 points on a number line. 10 particles which exist in a 1D world restricted to a line segment. I don't understand if I don't understand how you need I don't understand why you need to use every permutation for calculating Q. To me, it seems like you have 10 separate 1D coordinates, not a 10D space, unless there are some weird interaction terms with the particles. Even so, yeah, I don't know. Sushi Queb, thank you so much for following. Really appreciate it. Let's see. 10 separate 1D coordinates, not a 10D space, unless there are some weird interactions with the particles. This might make sense, but would be way clearer with a direct expression for Q. Let's see. To me, it seems like you have 10 separate 1D coordinates, not a 10D space, unless there's some weird interaction terms with the particles that you need to take into account. This might make sense, but it would be way clearer if we had a direct expression for Q. Yeah, I'm just gonna leave it there. I actually don't understand what that's getting at. I mean, I understand the overall point of this paragraph. I agree with. The point is to say that sometimes calculating Q is incredibly complicated, so we want to use some sort of Monte Carlo process to fix that. Now, where was that exist there? Oh, did I misspelled it, is what you're saying. There we go, this one, perfect. I thought it was a misspelling in the chapter. Exist, thank you. I'm surprised you can read that text resolution, actually. Sorry about that. Okay, so let's keep going. What's really powerful about the Metropolis approach is that you don't need to know the probability function itself. You just need to know you just need a function which is proportional to it. What this means for the Boltzmann distribution, that's a misspell of Boltzmann. Let's see. What this means for the Boltzmann distribution is that you only need to know the term. Okay, so let's go ahead and do a suggestion. Wait, perfect. That's super helpful. Boltzmann. All right, add review comment. You just need to know the term f of x exp raises a negative ex of t, and the Metropolis algorithm can bypass calculation of q altogether and use f of x to generate a function of x, which follows the probability density p. Okay, so here's my question. Maybe I don't understand what proportional means in this case. So let me Google what proportional means, because I maybe just don't. Proportional. I thought this. Okay, mathematics. Definition of proportional. Okay, so does this mean it's only by a simple scale relation? Or is there more to it than that? I think it's just a scale. Because if it's I think it's just a scale. Mr. Norai, thank you so much for following. Really appreciate it. Can we say scale instead of proportional? Yeah, it's just a scale. Okay, well, in that case, that's fine. All right, let's just keep reading. Then isn't that obvious? Okay. Let's go down. Where were we? We were here. Okay. It's more likely the value of x is... Wait. And the Metropolis algorithm can bypass the calculation of q altogether and use f of x to generate a distribution of x, which follows the probability density p. In other words, it can sample values of x in such a way that the probability of sampling x will follow the actual distribution p. The more likely a value of x is according to p, the more likely it will be sampled by the Metropolis algorithm. Wait 1 second. Grant is rolling in his grave. Why? I gotta be honest, like I wanted to double check to make sure I wasn't missing something there. You know, you always just Google things you think you know to make sure you're understanding something. I don't feel like that's too unusual, you know? It's like, maybe there's a way in which this phrase is being used that I don't understand, you know? And it's worth just double checking, you know? What was I going to say? There was something about that sentence that just didn't make any sense to me. Let me reread it again and see if I'm the only one. Okay. Where were we? We were here. So, this thing. In other words, it can sample values of x in such a way that the probability of sampling x would follow the actual distribution p. The more likely a value of x is according to p, the more likely it will be sampled by the Metropolis algorithm. But isn't that obvious from the equation? Because it's just f of x over a normalization. So maybe I would like to mention that. This makes sense because like we just do the normalization later is essentially what we're doing here. Like, and so I like literally just probe the function and then do the normalization later. Yeah, I think I want to mention that because I think like that's kind of where the, like, you know, the calculation of q is really annoying, but q is just a normalization factor. So just probe the function and yeah, that's all you have to say. The Metropolis algorithm can bypass calculation of q altogether and use f of x to generate the distribution of x, which follows probability distribution p. Maybe mentioning here, this is possible because q is essentially just a normalization factor. 1 second. Hey, Emrys, thank you so much for the subscription. Give me a second. Go ahead and put, how many female cows now? 20. Okay, 20 female cows. Let's go. All right, 1. Man, it's crazy that, you know, I've even been streaming that long too. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 female cows in the chat. Thank you so much for that. Really appreciate it. Again, I really appreciate all the support that everyone gives the channel. Hopefully we can get this Metropolis algorithm in by the end of the week. I wanted that in by the end of last week, but then we also added the probability chapter. So I think it's kind of fair taking 2 weeks for 2 chapters. I think is fine. This possibly excuse essentially just a normalization factor. So finding some other way to evaluate f, and doing the normalization after the fact can eliminate the Q calculation. I think it's important to explicitly mention this. Okay, let's add the review comment. Okay, now let me figure out if I can figure out what was wrong with that sentence. So in other words, it can sample. In other words, it can sample values of x in such a way that the probability of sampling x will follow the actual distribution p. The more likely a value of x is according to p of x, the more likely it will be sampled by the Metropolis algorithm. This fact dramatically reduces the number of samples needed to approximate the probability distribution. See, this is like one of those things, you know, like when you're introducing a topic, you kind of tease the topic a bit before like doing the full introduction. And I feel like this is a tease. It's like, well, okay, all we need to know is that we need to find some other way of sampling f of x. That's it. Then everything else kind of falls from that. In other words, you can sample values of x in such a way that the probability of sampling x will follow the actual probability distribution p. Right. I think we can ignore that second part of the sentence here. So let's just do this. I think we can remove this here. Okay, add a review comment there. Okay, of course, to be truly proportional to p of x, a Metropolis algorithm would still take some time before it converges. But it scales very well with the dimensionality of x, which in this case is proportional to the number of particles in the system, which can get very large in practice. Okay, furthermore, we often don't care about the entire space of possibilities. We usually care about a local region of p of x where the probability is relatively high. So you would have realistic positions for the particles. It turns out reality tries to exist in a high probability state. Who would have guessed? But the Metropolis algorithm tends towards high probability regions. It's good at sampling those regions and providing us a realistic collection of systems. Okay. Finally, the Metropolis algorithm can be modified or implemented in other algorithms and forms the basis of many advanced sampling algorithms. The most popular is probably the Metropolis-Hastings algorithm, which is fundamentally the same. Other algorithms that implement the algorithm are the Metropolis-adjusted Longevian algorithm, Hamiltonian Monte Carlo, to name a few. They're often used for physical systems that follow the Boltzmann distribution. Sorry, I'll go to another streamer because I need to distribute my video. Bye, have a nice day. See you, Mr. Noroi. Have a wonderful day. Yeah, sorry that we're still doing the chapter review, but hopefully we'll get back to the 4D Sims later. Yeah, see ya. So I'm going to be honest in saying that this paragraph doesn't make any sense to me. Like, I think it could be completely removed without losing anything in the chapter at all. Finally, the Metropolis algorithm can be modified and implemented in other. I almost feel like we could just completely remove this paragraph, and I'm just going to mention that. I don't know what's. Maybe it's because it was too confusing, but. One second. Okay. Let's see. The most popular is probably. Yeah. So this I need to change this. Other algorithms that implement the Metropolis method. Other algorithms using this method let's see, some other algorithms let's see that use this method are the Metropolis suggested Longevian approach. Okay, sure. Okay, I think the rest of it's pretty similar to what it was before. I can double check to see. I think the videos are better. Yeah, the videos are way better. Perfect. I think everything else is mostly the same. So I'm going to leave it at this for now. I think this is probably a good place to stop. So let me go ahead and just finish the review here. Say comment there. Am actually not. So what do I say here? I'm actually not sure if I understood the full. Let's see. It's like a mixed bag. So on the one hand, there were obviously improvements made to the chapter, but on the other hand, I'm not sure if I understand the argument for the example application. So I'm just going to mention that here. On the one hand, the Metropolis is looking way better. But on the other hand, I am not sure I fully understand the arguments. Oh, I misspelled arguments. One second. In the example application. Sorry if I was a little bit harsh there, but that's fine. Let's go ahead and submit the review now. Okay. Again, if anybody thinks that I'm being a little bit harsh, just let me know either here in chat or on the PR itself. Like, I fully recognize that sometimes I might like just not understand the point of a chapter or like a sentence. I might just read it incorrectly or something, and that's on me, not on them. Okay. I'm gonna be right back, guys, and then we're gonna hop into the 4D Galaxy simulation. So give me a second, and I'll be right back. Okay, I need to change the stream title. Let me do that right now. I can put my face back on actually while I'm doing that. Okay, give me a second. I'm going to change the stream title 4D Galaxy Simulation. 1 second. All right, let's go ahead and go. Done with that one. Right, so let's go ahead and introduce the topic, talk about where we're going with it and all that kind of stuff. So over here, let's go here, delete that. Bam. Okay, 4D Galaxy Simulation. What are we doing here? 4D Galaxy Sim. Let me get some water really quick. Probably should have had some water while I was on break, but you know, it is what it is. Okay. So what is the overall goal of a four-dimensional galaxy simulation? So the first thing to note here is that we're doing 4 spatial dimensions, which means this is not going to be an incredibly physical simulation. There's no such thing as right now, so far as our current understanding of physics is aware, we can consider a 4-dimensional space being Minkowski space, which is a combination of 3 spatial dimensions and some sort of imaginary time dimension of some sorts. But for our purposes, we're not dealing with that. We're literally doing 4 spatial dimensions, so maybe a 5D space, depending on how you want to count it. What we know is that if we take a 3-dimensional simulation and we let it evolve with time, it'll eventually create 2D spiral galaxies or disk galaxies, right? And so our stupid naive question is, what happens when you have 4D, right? So does this also create a 2D disks, right? And if so, does it create 2 2D disks? Because in 4D, there's 2 different directions of rotation. You can do a double rotation along the X, Y, and ZW plane at the same time. So is it possible, depending on what your initial conditions are, to simulate 2 double rotating disks, right? And so to do this, we have a bunch of little things that we need to work on. We have to have like initial conditions that actually satisfy, like certain requirements such that we could get a rotating disk at all. We've got questions of like, hey, what force laws are there in 4D, all this kind of stuff. So in order to get the 4D galaxy sim, we first need to do the 3D galaxy sim, right? So let's talk about that. All right. What I want to do now is create basically a very fast n-body simulator. Using the most up-to-date methods. And the hope is that we can actually do some new research here and essentially creating new spatial splitting structures. Sure. For, we'll say 2, 3, 4-dimensional space. So this is kind of what I'm looking for right now. Basically, I want to create an n-body simulator. Now, an n-body simulator is when you have n particles, where n could be anywhere from like 10, or technically 1, to 10 billion, right? Basically, the idea is you have all these particles in a room, all talking to each other, working together to move around. Like they could be bouncing in a box. They could be all mutually affected by each other's gravity, all this kind of stuff, right? So that's kind of what we're working on right now. We're working on the 3D simulation, and we want to make this as fast as possible, because to get the best 4D simulation, we're probably going to have to do like hundreds of different runs, each of which will take a very long time. And so to get our double rotating, 4D galaxy simulation or whatever, we're going to have to do a lot of work to get there. And having the fastest 3D galaxy simulator, hopefully in the world, if we can do that, that'd be amazing, would be the best way to ensure that we can get the 4D simulations that we want. Now, look, as far as publishable results are concerned, I can definitely see a publication here in the 3D stuff. We could do a 4D, publication as well. But if I'm being totally and completely honest, this is not going to get any citations. So we could do this. We could write a paper on this, but this is the one I'm mostly interested in, because I think this is mostly interesting for people who are doing these types of simulations. Improving n-body simulations is quite nice. But this one's super flashy, and doing a really flashy simulation is really useful for like what we were saying before, doing something fun and entertaining to get people engaged. So what are we doing here? So right now we're working on the 3D simulation. I read about kinematic data structures a couple months ago. Actually, I don't know what kinematic data structures are. Could you give me a link? I'd love to hear more about it. Okay, so here's kind of how the system works that we're working on right now. So we're going to be implementing something known as the Barnes Hut simulator. Barnes Hut. Okay, so here, imagine you have a bunch of stars in space. So we're going to do them in yellow. We're going to do them in yellow. And so we have all these different stars in space. Oh my gosh, give me a second. Star. Okay. Now, the idea is that each of these stars is influenced by all of the other stars' gravity. So we have all of this. This guy's influenced by every other particle in the simulation, right? And so in order to tell what the acceleration of this individual star should be, you have to look at every other n particle, right? And so to figure out the accelerations for every particle in the grid, you have to do an n-squared simulation, where you have to basically check every single particle that exists and check to make sure that you're moving forward appropriately. All right, let me go back a little bit. So what the Barnes Hut simulation says is, okay, well, this particle is sufficiently far away from these particles over here. So maybe we can treat these particles as just one giant blob with a center of mass somewhere and deal with these particles individually. And the way it does this is by basically creating something known as an octree or quad tree, depending on what dimension you're in. So what you'll do is you'll split the grid up into all these different quadrants or octants in 3D. Something like this, until every single particle has its own box. So something like this, right? And so what you'll do is you'll say, okay, well, this particle over here is far enough away from these guys over here that instead of seeing each individual particle, we're just going to read the root node over here. So we're just going to see all these particles as one giant box instead of all the little itty bitty boxes on the inside. There's obviously way more details there than just that, but the idea here is that we're minimizing the amount of computation by basically saying, hey, if you're far enough away, we're just going to approximate what you look like instead of, dealing with you specifically, right? And that's kind of how the Barnes Hut algorithm works. Today, we can go a couple of different ways here, and I'm not sure the best way to do this. One, we can implement an n-body simulator without the Barnes Hut improvements. This is good for benchmarking. It's something we need to do anyway. If we do this, I think we're going to want to do this with kernel abstractions and focus on and focus primarily on like performance, just getting some sort of parallel thing working on our GPU. Okay, the next thing we could do is we could do a full Barnes hut simulation. We did this quite a few years ago, but doing it again would be nice, and just getting something working there. Or 3, we could work on the visualization, which is also incredibly useful as well. Because if you have millions and millions of particles, doing the visualization here is non-trivial. Data I/O is probably going to take the longest amount of time, and so finding a way to write that to an image essentially involves histogramming of large data. Ooh, my power just flickered. But it doesn't look like I lost any frames. So anyway, histogramming of large data. And of course, we've talked about histogramming a lot recently. It's just one of those problems that keeps coming up. And so we can do any of these things. And I think I'm leaning towards this one because I just want to get something working. And then once we have it working, we can kind of, go from there. So just kind of get the infrastructure all working today because we're really just starting with this. All right, let me take a look at your links. 2 Curbs, sorry, I missed that. Look here. Okay. Over here. I missed an F at the end, but that's fine. PDF. Sure. I'll take a look in just a second. Basically, the data is considered moving, so it doesn't have to be as correct as much. Instead of putting just the particle's position in the data structure, you put an equation for the particle's motion. Interesting. Sure, okay, that makes sense, but if you don't have the equation specifically, let me see. This is actually quite interesting. Maybe it's something we could use even. So let's use Zernal PP. We're going to go into downloads, and then it's CS dash. Dynamic maintenance of kinematic structures. Stanford Universities, not bad. Let me see. I'm just going to scroll down to the bottom here. Sure, okay. Yeah, this could be quite useful, actually. It's not something I understand well. The thought is it might be useful here. So my fear, and I don't know if this is actually a true fear or not, but my fear is that, if you need an equation to specify what the data structure looks like, then I don't know if that'll exactly work because we don't have an analytical equation. However, this is something quite cool because we have been talking, and I know this is super lame, but we've been talking a lot about fractal compression recently, which is essentially an n-body simulator in and of itself for other reasons. And if we could combine the fractal compression stuff with an n-body simulator, i.e. working with an n-body simulator on a fractally compressed grid, that'd be super cool. And using a data structure like this, when we do have the equation underlying it for that fractal compression method, might be a good direction forward. Yeah, actually, that sounds quite cool. Let's see, I'm talking about stuff I don't know. So, there's, when people talk about research, right, there's a bunch of different people talking about a bunch of different things, right? And I tend to focus on the best possible outcome is this, but when you actually do research, it's like shooting for the stars or shooting for the moon, catching a couple stars type of thing. Sure. Okay. It's going to be very difficult to actually get this thing working, but if it works, it's amazing. And so that's kind of usually what I do with research, and specifically because this is an open research company, I feel like shooting as high as you can with as lofty of a goal as possible is really important for catching people's attention, right? So for example, instead of saying 4D Galaxy Simulator, I could say this, more like what it actually is, which is, let's say an n-dimensional n-body simulator for various applications, right? Sure, that's more academically interesting, but it's not going to catch as many people's eye, And so I have to keep in mind that there's this difference between the what I find interesting as an academic and what people find interesting in general, right? Okay, so here's what we're going to do. We're actually going to get this guy implemented first because it's going to be simple. I think we can get it done in the next 3 hours, and we can do some tests along the way to make sure things are working. So let's go ahead and hop into that. We're going to Control C here, and let's just get to it. CD projects, CD projects, Galilee. All right, CD projects, Galilee.jl, ls here, git branch. Okay, we're on the development branch. We can just go ahead and get started, make directory tests. Okay, now, I don't fully remember how run tests work in Julia. This is not because is because I'm an idiot, is what it is. There's no other reason. I just don't know how run tests work. I think you just write runtest.jl and then you just run tests. I think that's all it is. So cd into tests and touch run tests.jl. So here's what we're going to do first, because every single time I create a package in Julia, I forget. And I have to like steal stuff from other packages because I always forget. So here's what we're going to do. Let's think about the overall structure of this code and what we actually want to happen here. So journal, new page before. So what do we want users to actually write here for the n-body simulation, right? Let's talk about that. So one, we know we need initial conditions. I'm going to change the color here back to white. There we go. So one, we know we need initial conditions, initialization. What do users need when they're doing the initialization? Probably n, which is a number of particles, right? We probably need dim, which is the dimension. What else do we need here? Did you ever consider working at national labs as a career option? What are your thoughts? Yeah, so before I did my PhD at the Okinawa Institute of Science and Technology, I actually went to the Los Alamos Computational Summer Workshop or something like this. Look, I enjoyed it. National labs, if you as a researcher want to focus exclusively on research and you don't want to have to deal with the bureaucracy that comes with running your own business lab, which is not a good idea, which is what I'm currently doing, or all the bureaucracy that comes with academia, going to the national lab is a really good career option. The reason I don't want to go to a national lab is purely because I made a promise with myself when I was a wee little lad, 14 years old and just getting into research, that, when I was struggling to find research papers and struggling to learn how to code and really into Linux, I was like, you know what I want to do? I want to create an open research lab. I want all of my research to be 100% open. I want all the software to be open. I want everything to be open so people can interact with it and we can build this giant community. That's what I was thinking at the time. And national labs are often funded by the Department of Defense, at least in the US, which tends to mean that a lot of their research is not open. Now, that isn't to say they don't have open research that is done. They do have some open access work. They have some open source work to be done as well. But it's just, for the most part, the reason I don't go for a lab is because I don't like the level of security that happens there. On the other hand, working with a national lab is really, really nice because they enforce that you work 40 hours a week, which means you cannot work over 40 hours a week. As an academic, that is beautiful. You have so much time to do your own stuff. And so, look, maybe in the future, it's something that I'll consider more. I certainly have contacts in Los Alamos and a few other places, and I could consider doing that. But for right now, I'm not entirely sure that's the direction I want to go in. I really do feel that if I push this upcoming year and I get some really, really good, interesting research out, I can start to build my research company in the way I feel like I want to do. And I was thinking about it earlier today. I've been thinking about it for months, years even, as to what the appropriate balance is between contracted work and non-contracted work, how to do all of this stuff. And I do think I've got a decent business model ready to go. It's just a matter of getting the first few things done, and getting community support and stuff like that. And that's just a matter of me being consistent, streaming regularly, getting consistent YouTube content out, working with collaborators who, can really help me grow my audience and stuff like that. And then once I have that all done this year, I'm at the stage where and also publishing a bunch of papers, I'm at the stage where I can apply for grants. I can probably get good opportunities here and there. That's what we're going to work with. So national labs would be a wonderful career option for me if I were American. That's true. That's also true. National labs are very restrictive as to who they allow to work there. Now, my old boss when I was at Los Alamos was actually not American, but he got his American citizenship when I was there. So it's one of those things where I am also very privileged to be in the position that I'm in, knowing that, I have a super good background in a lot of stuff. And I probably could get a job in national labs, and partly that is because I'm an American. One other thing I do want to point out, though, is that this year, even if the Open Research Lab doesn't work out, part of the point of this year is repainting my CV to have projects on there that I'm actually very proud of, that will allow for me to, if I do want to go to a national lab, or if I do want to go to academia again, will allow me to get a position that I'm actually happy to do. Instead of the computational physics positions, more general computational science, or even like computer science itself, like computer graphics or something like this would also be quite interesting. Okay. So what do we want for the initialization here? I misspelled initialization. We want n, the number of particles, d, the dimension, which could be one, I guess we could do 1. Yeah, okay. We probably want 1. Okay, yeah. So number of dimension, this will be 1 to n. Where n is, I don't know. I don't know what to do about n. But like up to 4, I think is reasonable. So we want n, the number of particles. Now, we also want the force integrator. Okay, then we also probably want the force equations, which will be by default gravity, but you can also change the force to do a bunch of other things as well. Yeah, okay. So these are all things I want to read in. Now, for the force integrator, you know, it depends on what we want to do, but if we're just using gravity, then we could just use like Verlet integration or something like that for a first test. And then we can kind of work on more like robust force integrators from there. And just see where that goes, you know? So that's, I think, what we're going to do today is just start with Verlet integration, test to make sure that works. So we can only do Verlet integration if the force integrator is specifically gravity. But that's fine. That's fine for now. So let's just go ahead and do that. So I suppose, let's just go ahead and start hacking away and see what we can do. Okay. Let's go ahead and cd into source. L is here, and let's go into vi forces.jl. Let me go over here as well and open up the old Barnes Hut code that we had. cd project simuleos Barnes Hut. L is here. Let's go into vi barneshut.jl. Okay. Now look, we have the struct for particle and stuff like that. Let me just check the Verlet integration. So here we're reading in a particle, and we're basically saying, what do we need for Verlet integration? We're creating a particle P, and we're saying it's going to be 2 times part P minus part previous P plus part dot acceleration times dt. So what we're going to need then is we're going to have to read in function Verlet. Now, here's the other reason I wanted to kind of workshop it a bit. What are we doing for, like, what structures are we looking at here? So what data structures do we need? Let me go here, talk about data structures. Right, that's my next question. So before, I had a general idea for a struct particle, right? So the struct particle had a bunch of things inside of it. It had the position, it had the acceleration, it had the velocity, but then it also had the previous position, and like previous, I guess you could say kinematic bodies. And the reason it had that was because that's useful for calculating, like, you know, certain integration patterns and stuff like that. So maybe what I should do is I should create a general structure for kinematic bodies, and basically say, hey, these have a position, an acceleration, and a velocity. These can be n-dimensional structures, right? And so each of them, I want them to be tuples, is what I want them to be. I know probably tuples are a bad idea, and probably we're going to go away from them. But the nice thing about tuples is that they're they can be unrolled by LLVM a bit easier, and it's a bit nicer to work with in general. So I think that's what we're going to try. So we're going to function Verlet, and this is going to read in some sort of kinematic body, but we're going to work on that in just a second. And okay, so let's go right here, and let's go ahead to touch, actually VI, kinematic body. Should we call them kinematic body, or should we call them particles? I feel like calling them particles is fine. So let's do struct particle here, and this is literally just going to have, what is an n tuple? Let's go over here and just run Julia. I don't remember what an n tuple is. I greatly recommend against tuples if the language has support. At least in C++, C++ structs are much nicer, I think. But I'm not sure about Julia. Wait, wait, okay, so the tuple is going to be inside of a struct, right? So it's going to be like position here is going to be of type n tuple. The reason I'm doing this is so that we, my hope, and I don't know if this is entirely possible, but my hope is that we are able to directly turn the struct particle into an isbits type so that we can put that onto the GPU. That's kind of my overall hope here. If I could create a, it's not really great, is it? Because essentially when we put this on the GPU, we want every thread to deal with each individual particle location, right? So if we want every thread to deal with each particle location, then we probably want different arrays we probably actually do want different arrays, or like a 3-dimensional structure. All right, let's think about that again. It's a good point. It's just a simple tuple of XYZ. Right, that's all it is. Just n tuple something here. I don't know what the actual types are. I think we have to do something like this. Base. So position, velocity, and then acceleration. Okay, so again, today we're just going to get the n-body stuff done. We'll do the Barnes Hut stuff later. So n-body is what we're looking at. And we want something that's n-body that can be done in parallel on the GPU, which basically means every single particle. So let's think about that. I thought you wanted to make the entire struct a tuple. This is much better. Yeah. So let me think about something else then. So again, because we have to think about parallelization here, this idea of having a particle doesn't make too much sense, but having a list of particle positions makes sense. Again, we want something that we can access in coalesced memory, right? So like basically we want to be able to grab all of the X positions, all of the Y positions, all of the Z positions, all of the N positions, right? So I guess what we actually want is a set. Like we probably don't want a single particle. We want the set of particles instead of, we probably want a set of particles. So we have positions, plural, accelerations, plural, and velocities, plural. Parallelization, struct of arrays instead of array of structs. Right. Right, exactly. So yeah, this is what we want to do then. We're going to do particles, plural. We're going to do positions, velocities, and accelerations. And I feel like, okay, that's fine. Here's what we're going to do. I'm going to try to create a struct particles with a bunch of objects available in them. And I'm going to try to convert that to the GPU. I've got a feeling what we're going to have to do is change this into an array. No, they can't be arrays. It has to be either array or cuarray. So that's why I think n tuple might work, because I think that'll also work on the GPU. So let's go here and check that. So let's see if we can figure out the n tuple type really quick. I'm just going to make this big. Let's try to figure it out over here. Right and quit. Let's go into Julia. And let's see if we can figure out n tuples, because nah, it's not going to work either. Okay, we want them to be. Maybe we just don't have the particle struct at all. Maybe we just have 3 separate arrays for positions, velocities, and accelerations. This is probably off topic, but I was wondering why I use Julia language. Is it just preference? So there's a bunch of different reasons why I use Julia now. I used to use C++. That was my language of choice. I did my entire PhD pretty much only in C++. But Julia provides the same access to GPU hardware, which is what I predominantly use, in a much easier way. And it also provides libraries like, for example, kernel abstractions, which is something that we've dealt with before, which allows for me to write a single kernel that can execute on either the CPU or GPU, depending on how I dispatch it. That's incredibly useful. It's also just something about the community. The Julia community is usually quite welcoming for new developers and like new ideas and stuff like that. I know it quite deeply because I've been working with it for the past, since basically Julia 0.3. So the issue here is that C++, on the other hand, usually comes to be somewhat unwelcoming, right? Specifically in the area of scientific computing, I find that a lot of people, there's a particular way you kind of need to write scientific computing code that is dramatically different than how basically everything C++ and C++ 14 has been heading. It's quite hard to write good C++ code and also have it run on supercomputers quickly. And so Julia just kind of works for what I need it to work for. It's fast, efficient, it's easy to write. That's why. So you don't lose any performance, and it's easier to write. That's ultimately the reason. And again, I do recognize that it's not as useful for a lot of other areas. Like you can't do web development with it like you can with JavaScript. You aren't going to do operating system development like you're going to do with C++. But overall, Julia is quite a nice package for scientific computation. 3 arrays or a structure of 3 arrays are equally fine. Right. So my issue is not with the data. My issue is with the fact that we can't call it an array because you specifically have a different structure for the GPU, which is a Q array, right? So my question is, how do I transfer that? And I could do n tuples, but obviously I don't want to do n tuples. Basically everything in, I could just not type them and just have the compiler type them. That would also work. Maybe that's what I end up doing. Yeah, that's what I'll probably end up doing. They just won't be typed. I hate doing that though. Maybe I could just do union. Yeah, I just do union. That's what I do. So let's do union of... I don't like this either, but it's okay. Array, Q array. I think this will work. And we do the same over here. There, and we just do union of these two. So it's either one or the other, and I think that should be fine. Paste there. Oops. And then we also paste here. Perfect. I think that'll work. Let's just try to see what happens if we read that in. So we're going to do Julia, include particle, 1 second, .jl, CUArray not defined, right, okay. Using CUDA, and then do it one more time. This does mean that CUDA is a hard dependency, which is fine. It's so frustrating. Yeah. It's legit. It's just a an issue there. Okay, so here's what I'm going to try to do then. I'm going to try to create a particle. So P is going to be equal to particles, and we're going to read in Q array of, let's just do zeros of 10. Q array of zeros of 10. 1 second, and then Q array of zeros of 10. Sure. That should work. Perfect. And let's do the same for arrays, and it should also be fine. Okay, I'm just double checking. Perfect. Okay, so we can at least create the data structure. This will probably be fine. We'll have a position and previous position. So this leads us to an interesting question. How do we write our force integrator? So let's go into vi forces.jl. When did you, that is so frustrating. When did you transition to Julia? How did that journey happen? I presume you started with C, C++, Python. What features are important for when you select languages for a project? A super good question. I'll go ahead and ramble a little bit about this one as well. So just for the record, I'm incredibly biased based on scientific computation. So like, for example, when I was in high school, I did C and C++ and also HTML, if you can count that, because I was really into game development. And for some reason, me as a kid was like, C and C++ are the languages that we need. And that's what I learned. Obviously, look, I took the hard route. I loved C and C++. I didn't know how to make games, but it was interesting, right? Then I kind of didn't do so much programming for a year or two. And then when I started again as undergraduate, I again picked up with languages like Fortran. C++ was always there, a little bit of Python. We also did some IDL. And these are the languages I primarily used, stuff like that. So these were the languages that I used primarily during my undergraduate. During the PhD, I then pretty much focused primarily on C++. And the reason I focused on C++ was because I was interested in GPU computing. And GPU computing was basically all done in CUDA. CUDA was predominantly C++. Now, there was also OpenCL and OpenGL and stuff like that. MATLAB is a language that I unfortunately had to touch, but I genuinely hate with a burning fiery passion. I genuinely hate the language. There's absolutely nothing that can redeem the language in my mind. But anyway, we're just not going to go into it because it used to be a meme that anytime people would bring up MATLAB, during the PhD, most of my lab used MATLAB, and literally anytime anyone brought it up around me, I would just get pissed. And look, I know I had to manage my anger, but just the reason I was so angry at MATLAB is because I did not particularly like the direction of my research at the time. And what happened was pretty much everyone else is using MATLAB, and I fundamentally knew that the problems that I wanted to solve could not be solved with MATLAB. You needed something that could do GPU computing. You needed something that could do like more robust calculations. That's the type of stuff I actually genuinely wanted to work on. And so when people were like, just use MATLAB for that, it was just a constant reminder that I wasn't doing the research I wanted to do. And that was why it was so frustrating to me. So every single time people said, I'm using MATLAB for this, it's fine. Like, it's totally fine. It's a valid language for them to use for the stuff that they're doing. But it was super frustrating for me because it meant that it was just a further confirmation that I was in the wrong research area and that I needed to change. So that was why I don't like MATLAB. The language itself is very frustrating to use for other reasons, but the main reason was a social reason. Coup de fortune, I hate MATLAB too, but I work in controls, so I had no option. I'm hostage in that sense. Yeah, I mean, that's fair. Have you seen Twitter page? I have seen the Twitter page. That one's actually quite good. Definitely is a great language for control. I did Simulink a lot for numerical modeling. Anyway, point is, look, MATLAB cannot do the stuff that I actually want to do with research. It tries to do some GPU stuff, but like, look, when you're talking about like, massively parallel computations on a distributed supercomputing cluster, MATLAB is not the right tool for that job. You can make arguments for, potentially using it in that scope, but that's just not what it's meant for. And so, that's the tough stuff that I am particularly interested in, and eking out every little bit of performance I can. And that's just not the world that MATLAB is made for. Anyway, I'm not putting MATLAB on this list because, again, it's not that I didn't use it. I did use it. It's just that I hated every moment of using it. So I'm not putting this down on the list. So during the PhD, I predominantly did C and C++. There was a comment up here about game dev. Where was that comment? Just curious, have you ever worked with game dev people? So personally, I have not done too much game development. I've had ideas, like I've kind of wanted to do game development to some extent, but the problem with game development, at least for me, is that, like, creating a physics engine is super fun. Working with the back end is also kind of enjoyable to some extent. But the moment you start putting art assets on it, it just gets so hard and boring. And it's just like, it's the same with pretty much everything front end. It's like I have tremendous respect for anyone who does any type of front end development, because it's just so tedious. It's like, that's what I think about game development. It's just so incredibly tedious. It's like you take all the fun out of it. And it's just, I love creating stories. And I think video games are great ways to tell stories. And so from that, like, I like the storytelling aspect of it. I like the back end part of it. But that middle ground, when you're making art assets and you're, trying to make sure that, like, you're pixel perfect with this thing, make sure there's no clipping, like, all this stuff is super, super tedious. And I know some people can love it. And I just have the utmost respect for those people because it's so much work, Anyway, I'm a game dev student, but my focus is engine development. Right. So engine development, like, I feel is one of those areas I could kind of enjoy. The big reason I don't do game development is that, like, I don't know. Like, I play some games. Like this morning I played Ring Fit. I love Ring Fit. I play Digimon World every now and again. Guild Wars 1, I don't play Guild Wars 2. But, when it comes down to it, it's like, I don't know. I'm not a gamer. Like, I don't understand gaming as much as I understand other mediums. And for me, I love doing new things that people haven't done before. And sure, creating new game engine developments and stuff, like, this is quite nice. There's a lot of interesting papers in the area, like specifically in computer graphics and stuff, but it's just not, I don't know, it's not enticing enough as a researcher to really go into, And I find that doing new novel things, like reading papers and figuring out stuff that people haven't figured out before, this is really where my passion is. Let's see. Funny thing is, though, studying game development, but now interning at a profiling company. Right. Like, that's the thing, though. Like, it's kind of universal applications. You can use some of the stuff that you're learning in the game development, see in other areas as well. Anyway, we're super off topic. The question was, what languages do you know? Why did you switch to Julia? All of these things. So again, as an undergraduate, I did Fortran, C++, Python, and IDL. As a graduate student, I mainly focused on C++ with GPU engineering, and then at the very end, we did Julia. The reason was that Julia just wasn't particularly popular up until basically the end of my PhD. But the big reason I started using Julia more was because its GPU capabilities, the general purpose graphics processing unit capabilities, were just phenomenally easier to use than the C++ tools, right? Like you have to use NVCC with C++, and you have to build all these libraries, and it's just a pain. Like getting HDF5 to work on C++ versus Julia is just so much easier in Julia. And basically all the tools for distributed computing and everything else. Like as much as I say I like to work on the level, like I kind of was saying that I don't like working out with MATLAB because it doesn't allow me to work on the level that I want to work on. Julia allows for me to work exactly on that level. So I don't have to go so deep in the weeds as I did with C++. And, I can still attack all the problems that I want to attack. So it's just like at that perfect level of letting me dive into the actual details, looking at the source code, figuring everything out, while also giving me access to hardware. But it's also not super complicated. It's not like, you spend all your time making a makefile or like figuring out how to get this to build on different clusters and all that kind of stuff, Like it's just at that level where like it's easy enough to use that I don't feel frustrated with it, but it's difficult enough. It's meaty enough. It's in-depth enough that I can still tackle the problems I want to tackle. So that's why I like Julia. That's why I made the switch and why I've been using it for a while. Now, is it the best language for everything? Definitely not. I know a lot of researchers who don't like using it for various reasons, and I respect that, I think it's really up to you and what you want to do, what research you want to do, what projects you want to work on, what language you think best suits you, And so like someone mentioned, you could use Fortran with CUDA. That is actually a thing that you could do. But I never went into that. By the time I was doing the PhD, I was heavily in the C++ camp, and that's just where I did all the GPU engineering. So anyway, yeah, I'm a very strong defender of Julia. I think is a great language, and I think everyone should give it a shot if they're in the same area that I'm in. But I also recognize, look, if you've got a huge code base that is like 10,000 lines long or something longer. I know that's actually not that big, but in the scope of scientific computing, that can be quite long. Don't switch that to Julia just because, you think it's going to be slightly better for this or that. Like, stick with the code that you have before you, but if you're writing a new code base, maybe consider Julia, Anyway, that's the rant about Julia. Sorry about that. I've completely lost what I was doing with my life. Okay, right. So the next thing I want to look at is Verlet integration. Okay, so we found that we can just create the struct for all the particles, which is fine. So what we want to do here is we want to read in kind of like an individual particle. And this is where things get a little bit, I'm not sure the best way to do this actually. So probably what we want to do is we want to create a separate Verlet stepping method. Yes, this is probably what we want to do. This isn't the best way to do it. I'm just going to do it this way. So we probably want to do position 1, position 2, velocity 1, velocity 2, acceleration 1, acceleration 2. Okay? And then in here, what we're going to do is we're actually going to read in another function here. So it's going to be function Verlet. And what this is going to read in is a set of particles. So it's going to be pset. I don't know what to call it, but I'll call it pset for particle set. 1 is going to be particles. Okay, and then pset 2, which is also going to be of type particles. All right, and we're just going to call this function for that one. This allows me to create an overall like Verlet function that allows me to work on all the particles that exist, and then one that works just on individual pieces. So, and here what we're going to do is just call Verlet. How are we going to do this? I think it has to be Verlet dot of particles. Pset 1 dot positions. That's very long. And then pset 2 dot positions. I think this will work. And then we have to do the same for velocities and accelerations. I think we can just call that, and that should work. Yeah, let me just do it this way. dt comma sure. Oh, wait, what? Oh, I see. I'm missing a comma at the end there. All right. Right. Here as well, and then $$ over here, there, and then we're going to do velocities. Velocities, and then we do accelerations. And then we do accelerations in here. So I'm going to actually have to ask how Julia works in just a second, because I don't know if this is going to work or not. I really don't. So this is going to be moving everything forward one time step. So let's think about how that's actually going to work. So I guess what we're going to have to do here is we're going to have to create like a... So positions, accelerations, and velocities can be n-dimensional structures. So that means that they can be 1, 2, 3, or 4-dimensional. We'll have to deal with that dimensionality in a second, but for now we're just going to deal with up to 3 dimensions. The reason bigger than 3 dimensions is a pain is because for GPUs, you usually only have like 3 dimensions to work with, the X, Y, and Z dimensions. To go beyond that, you have to do like create your own special accessing patterns, blah, blah, blah. But I think by the time we have to go beyond that, we're also going to have our own gridding structures by using like a type of space filling curve. So we'll deal with that later. Okay. This is where I forget everything about Verlet integration, and I have to go to the algorithm archive, which I wrote 5 years ago. So let's go here, remove all unfinished, go to the algorithm archive, go down here and go to Verlet integration there. Take a look at some source code. Okay, here we have the source code. I'm just gonna grab this guy. Actually, let me just grab this entire thing, function Verlet, and let me see what it actually does. So here is my function Verlet that I wrote before. So it takes in a position, which I specified as float 64. If I were to write this now, I probably would have just specified it as a number, not as a float. Acceleration and the time step. Of course, time step. Why am I such an idiot? dt. And in here, we're also going to read in dt. Okay, perfect. Okay, so what we're going to do here is we need to create a temporary position, but it doesn't seem to take into account velocity, which is fine, right? Because Verlet integration specifically is a way to, right. So we're going to have to calculate velocity as well. So I'm probably going to read in an optional argument in here, which is going to be like calc velocity. This is going to be calc velocity equals true. I don't know. So in here, we're just going to do the same thing here. I have an optional argument for calc velocity equals true. Sure, we'll do it that way. Okay, I'll think about it in just a second, because actually for Verlet integration, we can just drop the velocities here entirely. So let's just go ahead and drop the velocities. Good, okay. And then that means we don't have to recalc velocity in here. We need a separate argument here for calculating the velocity, and we'll do that now. So if calc velocity, okay, and there. Okay, now Verlet integration only works with the kinematic equation, which is kind of a downside, but that's okay. So we're gonna do time is gonna be plus equals dt. Sure, okay. So now we do the position. The new position is going to be equal to the position times 2 minus the previous position plus the acceleration times dt. Perfect. So how do I imagine using this? I imagine having... This is after we've calculated the acceleration, right? So we already have the new acceleration. We have the old acceleration, although frankly, I don't know if we need the old acceleration, but I guess it's fine. So all I'm trying to do is I'm trying to calculate where this new position moves to and then move the old position. So basically I'm just trying to move the old position in. So the easiest way to do this is to say temp position is going to be equal to position 1. Temp acceleration is going to be equal to acceleration 1. And then we're going to go in here and just say the position 1 is going to be equal to, this does mutate the data, and I'm not sure if I made the struct mutable, but that's okay. We'll deal with that in just a second. So position 1 is going to be equal to position 1 times 2 minus position 2 plus acceleration 1 times dt times dt. And then we're going to go down here and say position 2 is going to be equal to temp position. And we're going to say acceleration 2 is going to be equal to temp acceleration. However, we probably can just do is equal to acceleration 1 here. If you can sim a 4D galaxy in our 3D galaxy, does that mean our galaxy could be simulated in a 2D galaxy? So what we're going to have to do is we're going to have to take the 4D simulation and project it down to 3D for the visualization. So it's going to be purely 4D. As far as can you simulate our 3D galaxy in 2D? Kind of, right? Because our 3D galaxy is on a 2D rotating disk. So in some sense, if you do a 2D visualization or a 2D simulation, you can probably get very similar results. But that's not what we're doing here, right? Like ultimately, the test here is whether we can take a big 3D simulation, turn it into a 2D disk. So similarly, we're going to take a large 4D galaxy simulation, see if we can simulate, again, either a 2D disk or two 2D disks. It kind of depends. So let's go ahead and remove this here. So what this is doing is it's saying we have a temporary position. Then we say position 1 is equal to whatever it was before times 2 minus position 2 plus acceleration. So we've modified position 1, position 2, and acceleration 2. But we have not modified acceleration 1. I mean, you can always project to a smaller dimension, right? Yeah, but the simulation might fail if you project to a lower dimension. But backwards is not possible. Right. Right, but some structures you can only see in n dimensions. So if you project it down to n-1 dimensions, you might not see those structures anymore, right? And so for that reason, you might, you need the full n-dimensional simulation. You can't do the simulation n-1d. That's what I was trying to say. I'm not sure if that point got across, but the short answer is we could technically simulate our 3D galaxy in 2D, technically because of the way our galaxy looks. But you couldn't simulate our 3D galaxy in 1D, or a 2D galaxy. I'm imagining a 2D scientist streaming on a 2D Twitch talking about simulations in a 3D world. Well, to be fair, I mean, right now I'm just a character on your computer screen, right, which is inherently 2D. So we're actually talking about 2 dimensions ahead of what you can actually see. I have a visualization on my YouTube channel for understanding 4D, the Tesseract, which is by far my most popular video. It's got 3 million views. I don't know. It's got a large number of views. And man, the comments on there are just insane. Talking about how clearly I could have maybe done a better job of explaining it, but I think I did a way better job of explaining it than all of those people who are they're like, okay, in 4D, you need 16 vertices to represent. It's like, no. Check out that vid. To be fair, though, to be totally and completely fair, the video could have been done better. It was made 5 years ago, right? But I think it gets a lot of negative press, which I don't particularly feel is warranted. Okay, so the temporary position is equal to position 1. We say position 1 is going to be equal to whatever it was before times 2 minus position 2 plus acceleration 1 times dt. Then we set that. Perfect. So this assumes that the acceleration is defined before the calculation of relay integration. So that's an important thing to mention here. We also need to do the force integration step, but that's okay. Let me go ahead and delete these lines down here. dg. And in here, we're going to do our velocity calculation. So we're going to say velocity 1 is going to be equal to, what is it going to be equal to? I wrote it in the algorithm archive. It's going to be x. Oh, it's going to be the change in x over change in time, obviously. So velocity 1, where were we? Oh, am I in the wrong? Here it is. Velocity 2, wait. Nova Train, thank you so much for following, really appreciate it. Velocity, fine. We're going to say temp velocity is equal to velocity 1. Then we can go in here and say velocity 1 is going to be equal to the change in x over change in time. So this is going to be p set 1. I mean, yeah, I guess this is fine. It's going to be p set 1 dot positions. Sure. So this is going to be equal to p set 1 dot velocities. Fine. I'm going to have to do copy. of this. And then in here, we're going to say pset1.positions. Maybe I'd do a for loop. No, we're going to have to do it this way anyway. It's fine. So pset1.positions minus pset2.positions. Then we want to divide that by dt. And then we say velocity 2 is equal to temp velocity. And probably want a dot equals here. And probably a dot divided by there. And then we're going to do velocity 2 is going to be equal to dot equals temp velocity. That should work. Okay. Now look, the Verlet integration doesn't have the velocity calculation inherent in it. Fine. Fair enough. So we have this separately. So now we have to find a very simple n-body determination of your acceleration. That's the next thing we need to do. And then the hope is we can just set like 100 particles on a grid and run it. So that's what we're going to do. We're going to do a very simple n-body simulation. Now for visualization, okay, we'll think about visualization later. So today we're not dealing with visualization. We're just dealing with, probably want a simple test. We want a simple test where, I need to think about that. Is that a minus sign after the equal sign? There is. You're correct. I need to change that. Thank you so much. I missed it. I just typoed. Okay. So this is going to be our forces file, which means probably do want acceleration in here as well. So function, find acceleration. Now, this one's going to be a bit weird. Here's what I'm going to do. I'm going to do find acceleration, which takes in pset1 is what it's going to read in. Just pset is what it's going to take into account. And this is going to read as particles, something like this. And then what we want to do is read in an optional argument, which is going to be type, I guess is what we're going to call it. I don't like that. Sim type, whatever. And this is going to be equal to, by default, I guess n-body by default is what we're going to say. I misspelled function. Okay, so now what I want to do is create a separate function for n-body, and then we also want like separate functions for like octree and stuff like this. So, you know, we're doing n-body today, and we should be able to just dispatch this on the function. So in principle, we should be able to do sim type. In fact, we might not need this at all. We might just be able to do sim type of, okay. D, let me just remove these guys and just create function n-body. Okay, this is going to take in a pset, which is of type particles. All right. All we care about here is the particle positions. So we could actually make it so n-body only acts on particle positions. Does that matter? Yeah, it matters. It does actually matter. Okay, so we're going to do what I did before, and I just erased. So function, find acceleration. And this is going to be reading in pset. Do we need the old acceleration for anything, or do we just need the new accelerations? That's my question. Do we need the old accelerations for anything? We don't. Probably. We just need to update the new accelerations, which is fine. Okay, that's fine. So I'm going to do pset, which is of type particles, and then we're going to do sim type, which is going to be just roughly n-body is what I'm going to call it. Here and here. Okay, and we're just going to make sure this is an optional argument. Okay. Okay, I'm not sure exactly how we're going to write this, but we probably want to do sim type on. I guess I want to do pset dot accelerations. It's going to be equal to sim type on pset dot positions or something like this. And this allows for me to dispatch on different potential ways to find that acceleration. So right now we're just doing it in an n-body way. And we go from there. Gotta go. See you, Levi. Have a wonderful afternoon or evening or whatever time it happens to be. Hopefully, I'll see you around next time. We should get some sort of result out by the end of today's stream, just like a very quick end body simulation. And then hopefully we can do some, I don't know, I need to put a test in there as well. But yeah, hopefully I'll see you around next time. Thanks for stopping by. Okay, so we have function end body here. And so what we're going to do is we're just going to go through. Here's where I do know. Okay, so we're going to get something working on the CPU first, and then we're going to try to dispatch this onto a GPU kernel after that. So let's get the CPU version working right now. So for I is equal to 1 to length of particles. All right. And here. And we have to create a list of accelerations. So it's going to be equal to, the accelerations are going to be equal to, here's what I'm going to do. I'm going to make this work this way. This is going to read in accelerations and positions. And then in here, we want to make it so this is done this way. So we're going to do pset.accelerations. Perfect. That'll help out. Wonderful. So we have all the accelerations. They should all be of the same length. We can check that later, but it should all be of the same length. So the next thing we're going to do is say for j is equal to 1 to length of particles. Okay, and in here we want to define temp acceleration is equal to 0. And here, okay, so now what we need to do is basically update the temp acceleration. So we're going to say, what is this? Accelerations of I is going to be equal to, what do we want here? Accelerations of I are going to be equal to temp acceleration. Sure, I should at least. All right. Now we just have to update the acceleration. So in here, we're going to say temp acceleration is going to be equal to position of one minus position of the other. So it should be positions of I minus positions of j. Okay, now here's where we do need to be able to read in a different force law. So we need to think about how exactly we're going to do that calculation. So probably what I want to do is read this into a separate function, which is going to be find acceleration, depending on what the force law is. So in here, I guess we're going to read in force law is going to be equal to, I guess it's going to be gravity. Sure. And we're just going to create a new function for gravity. All right, and in here, and we're going to read in an optional argument here for force law. It's going to be equal to gravity. Perfect. And then here we're just going to say force law of position of I, and then positions of j. Sure, that should do it. And then for gravity, what we're going to do here is say return temp acceleration with that, and then we're going to return that's something over r squared. So it should be, it's like GMM over r squared. Now, how physical do we actually want to be here? Is the next question. I don't actually know the answer here. Probably, should we have the gravitational constant actually in? No, I'm not gonna, screw it. No gravitational constant, whatever. No gravitational constant, we'll do this later. So it's gonna be return 1 over, it's gonna be position, we can call it pose 1, pose 2. Okay, it's gonna be return 1 over r squared, so it should be position 2 minus position 1 squared. I guess I'm just going to do a multiplication. Position 1, 2, minus position 1. All right, put this in a Bale parentheses. There we go. That should do it. No idea if this is going to run. Okay, so the next thing is, what would I do if I wanted to make this into a kernel? I think it's relatively straightforward to turn into a kernel. I just have to remove the for loop, and then it's done. So let's just go ahead and do that right now. That dispatches... Okay, no. We're not going to do that right now. We're going to get it working on the CPU, then we're going to work on putting this in parallel, because I don't know how to do the dispatching functions just yet. But we'll worry about that in just a second. So right and click there. So I think the forces.jl worked. We can find the acceleration of every point in time, and then we can move the particles forward with Verlet. So we find accelerations, and then we run Verlet on, on everything. No potential smoothing. Not right now. I mean, we're literally doing something super basic. But also, what is potential smoothing? I should know what that is. I've heard it before. I've read about it before, but I thought this was for, this isn't for smooth particle hydrodynamics, is it? Yeah, but we're literally just getting started. So, we'll be adding a lot more tricks later. Okay. Gravity, n-body here, reads that. Relay integration, okay. So let's go here, write and quit. What do I have here? ls initialization, mesh, and then I guess I have run. What should I call it? I guess I should call it simulate.jl. If you're going to do 1 over r potential. Right, I agree. Yeah, that's something that we'll have to deal with later. But I was going to deal with that in a slightly different... So I don't know, I actually don't think I don't know what the term potential smoothing means right now. But usually, what I do is I do like kind of a hard sphere collision at some point, or something like that. That's what I used to do. Although that's not going to work for a galaxy simulation. I understand that as well. So that's fair. Plumber smoothing. Right, we'll do that later. Right now, we're not there yet. So, okay. So for running this guy, what we're going to want to do is create a simple function, which is going to be, I don't know what to call it. I guess we'll call it run sim with an initial set of particles, I guess. Okay, so how do we actually want to do this? I guess it's going to be called Galilee. So I guess we just call Galilee.run. So we're just going to call it function.run is going to be run, and it's going to take in a set of particles. All right, and here. And what we want to do here is, I mean, it could just be Galilee.run with the appropriate parameters in here. So it's going to be Galilee.run, and it's going to read just all these are optional arguments. N, oh no, N should probably be decided. N, and then the optional arguments are going to be force, law, which is going to be default to type gravity. And then we also had another thing that was default. What was it? And then it's going to be sim type, which is going to be of type. What is it going to be type? It's going to be of type. What did I call it? I called it n-body. Sure. Right now that'll work. N-body. 1 second. N-body. And then we also need another one, which is going to be the force integrator. We have the force law, but then the force integrator is different. I guess I'm going to call it integrator is going to be equal to Verlet. Something like this. All right. So the first thing we need to do is initialize n, and then we're going to go over here to particles is equal to that. Okay, again, we're just kind of slowly but surely getting the code there. There's going to be a lot of just like hand waviness that goes around here. So for this, I know we're probably going to have to do include forces .jl. Actually, wait a minute. No. This is all going to be done. I think actually what I want to do here is just export run. I think that's all I want to do, because I think this is all going to be done in Galilee.jl here. And then in here, what I want to do is using CUDA. For now, I think we'll also do adding CUDA kernels, but maybe what I'll do is kernel abstractions. Let's see. For now, that's what we need. And then we say if has CUDA GPU and using CUDA kernels, something like that. All right. Simulate.jl, so we have function run. Oh, I need to add that into Galilee. Okay, simulate.jl. Okay, so run, we initialize all the particles, which we haven't created that function yet. Let's go ahead and do that now. Nope, let's go ahead and go here. So the next thing I want to do is we've initialized the particles. So after initializing the particles, what do we want to do? We actually run it for various time steps. Now, how many time steps do we have? So we also want to read in probably dt and the time steps. So n is the number of particles, t, I guess, usually I use n kind of willy-nilly to mean number of particles and different things. So let's actually do this separately. Particle number, time step, and then we're going to call it, see, number of time steps, iterations. I realize this is super bad notation wise. I'm so sorry about that. I'll try to fix it later. Let me move the optional arguments down a line just so it's a little bit nicer. And then here is going to be particle number. Okay, so next thing we want to do is for I is equal to 1, 2 iterations. And here, again, this is all stuff that we can fix later, but like this is literally just getting the first, like, something working. That's it. We're just trying to get something working. Okay, and then we're going to do for I is 1 to iterations. Literally all we're going to do is take each of the n particles and move them forward a single time step. It's all going to be on a single GPU. We'll worry about parallelizing it later, and just go from there. Okay, so how's this going to do? How are we going to do this? So this means we're going to have a set of particles, and we should just be able to run, find accelerations, find acceleration here of pset, because I've been calling them all pset. Sure. And then the next thing should just be, so the next thing should be that we just run the integrator. So it should be integrator on pset, which should update the positions in the integrator. And then we should just write it out. So I'm going to also do another output method in here. Oh, so let's do, I guess I'm going to put a new line for output method. I guess if there is an output method that exists, then we call it. Otherwise, we don't. Sure. It's going to be equal to file output. Maybe for now is what we'll do, because we're going to have to plot this in GNU plot. There's a bunch of other ways in which we can do the output, which we'll worry about later. So if output method is equal to file output, and here we just write all of the points to files. So probably we need to use delimited files. Let's go into Galilee.jl, and then go here using delimited files, right, quit, Julia _ project. And let's do add delimited files. I think we can probably get the n-body simulator done today. Like, we got 2 more hours left in stream. Well, 1 hour and 45 minutes left in stream. I think we can get like some super basic n-body simulator working, and go from there. Let's do Control D, and we're gonna do this using delimited files. Perfect. Okay, so now we're gonna do simulate.jl, and this we're just gonna use, I think it's write DLM. And we're literally just going to write out all of the positions. We could do multiple like things here, but I think it's just write DLM, and then we do positions. I think we can write DLM twice, can't we? Can we do... Yeah, so we just write DLM the positions. Let me see what happens if I do the following. So let me do A is going to be equal to... let me do it over in this terminal so it's a bit bigger. Julia, using delimited files. Now we're going to do A is going to be equal to just some simple array, 1, 2, 3, 4, 5, 6, 7, 8, 9. It is raining, and there's like a bit of rain hitting the window. I think these need to be spaces. Okay, perfect. Now I'm going to do write DLM. Can I do this? Check. .dat. A. Of course, that doesn't exist. Let's just use this one. And then if I do it again, I think what's going to happen is we have to do two separate... Yeah, okay. It'll rewrite the data file. So I want to do delimited files, appending to a delimited files. To file delimited files, Julia. Let's see if I can find that. Delimited files here, write DLM usage. Okay. Now let me see if I can just do append. Yo, what up? Just came in. Are you doing an n-body simulation for arbitrary dimensions? Yeah, kind of. Yeah, so what I'm particularly interested in here is there's a couple things that we're interested in, right? Like physically, is the interesting question, what happens in 4D with the galaxy simulation? Does it create like multiple 2D disks, multiple spiral galaxies that can double rotate? We don't know. Probably not, but like maybe there's something interesting there, right? But yeah, research-wise, what I'm interested in is creating new like spatial splitting schemes for like the Barnes-Hut algorithm and stuff like that to basically improve on n-body simulations as they're currently done. And so that's kind of what I'm working on right now. It's a relatively straightforward, like what I plan to do is use some of the spatial splitting schemes from the color quantization literature, which doesn't seem to be done too much, and I'm kind of wondering why. So we'll see how that works out. But ultimately, if we don't get anywhere research-wise with this project, it's okay, because kind of the point of this project is to go back to the color quantization stuff that we were doing before. So you were here a few weeks ago when we were doing the photo mosaic stuff and also the ASCII image stuff. I was talking a lot about all this. Well, all of that requires, the way I wanted to implement it, all of that requires a good color quantization scheme that is time dependent. And the only other simulation type that I could find that does time-dependent Oct trees were n-body simulations, specifically gravity simulations. So that's why I was like, okay, let's do n-body simulations first, kind of get this under wraps, work on our adaptive mesh refinement, all this kind of stuff. And while doing that, see if we can find some better spatial splitting schemes for the 4D galaxy simulation, for like higher dimensions, all this kind of stuff, because it's kind of like a nice thing to look at anyway. And then we'll go back to the visualization stuff after that. So we'll see how it goes. But yeah, we're slowly going through everything. It just takes some time. As far as the PR is concerned, I just went through the additions to the Metropolis chapter earlier today. Overall, like super good work. I think it looks way cleaner. But I might have sounded a bit harsh. I think there was like one example that I didn't quite fully understand. I was like, I don't know. Like I just didn't understand where it was coming from. And so I think just further explanations of where that's coming from, or maybe like changing out for another example, would do wonders to make it a little bit just slightly easier to understand. But that was the only bit. I think once that's cleaned up, I think the probability chapter is pretty good right now, and the Metropolis chapter is also pretty good. So I think it's pretty much, at least on my end, without looking at the code too much, the chapter is pretty close to being ready to go, which I'm quite happy with. So good work on that. Okay, so what I'm looking for is how to append to, based.append, how to write out multiple, I want to write down multiple arrays to the same file is what I want to do. What I might just have to do is write my own write method, maybe. Yeah, that might be what I have to do. Okay, wait, this was not what I was looking for. Delimited files, read DLM. So let's go into write DLM. Sure. Read DLM, write DLM, Come on. There it is, right DLM. Delimited is T options. So what are the options here? I'll need to check for notations because they seemed a little weird yesterday. That's fair. I mean, look, the thing is with chapters, it obviously takes a lot of work to get these in, specifically because we haven't been getting them in, and this is like the first chapter that we're really like, finishing up. I need to check on Lick's chapter as well because I think that one was ready to go. Just was like some small changes. So I'll check that, but I think they're basically good to go. So we do read DLM, we do open, write DLM IO, XY. I think I'm just going to have to write my own write function, which is not particularly great, but that's okay. I'll just do that now. Control D. Control D. There we go. ls here. I'm just going to create an io.jl. Yeah, io.jl. Is going to be write to file. Function write to file. And this is going to take in pset of type particles. And here, actually, in fact, it's just going to take in an array. This is going to take in A, which is going to be any n-dimensional, 2D array specifically. I don't think you were harsh, but I'm just not sure how to make the interpretation of Q clear. An explicit integration example. Right, so I'll talk about that right now. Let's just go ahead and hop into it. Let me go here, right and quit, and let's go into CD projects, algorithm archive, ls here. There was one particular paragraph. I genuinely had no idea what you were talking about at all. Like I was really quite confused as to what was happening. Let me do npm run serve here. And I think that example could be completely removed. And it wouldn't lose at all, anything. So let me go here, open up localhost. And actually, I didn't know if it was, let's talk about it right now. So let's go to localhost here, and then we're going to do Metropolis algorithm should be right under Monte Carlo. Perfect. Right, so the question was this guy right here. So let me move in, make it a bit bigger. Bigger? Sure. There, scroll down a bit. Okay, so this guy. So we see that Q is unfeasible to calculate. Imagine that there are just 10 particles, all of which exist in a 1D world, restricted to a line segment. This means that the energy E of the system is a 10D function. So that I was already confused about this step. I didn't get this. Whatever it was, I think it is quite useful because it is a really nice explanation for why you might not be able to calculate Q. But I didn't buy that it was a 10D function. I don't understand how the energy here is 10D. Isn't it 10 separate 1D functions, not a 10-dimensional function? So that was my immediate question. I didn't understand that. And so then the next thing was, now imagine that we divide the 1D line segment into 50 different intervals. It took me a second to figure out what you meant by this, but you meant that you're quantizing each X such that it's, one of 50 different positions, which you say right here, but it just took me a second to figure out what that sentence meant. And then I said, this is equivalent to, you said, they were right. So just saying that they were interacting, and then saying what interacting means, which means if one moves, it influences the movement of every other particle on the grid or something like that, would immediately be okay, I see now. So that was kind of confusing to me. And so then if you say that they're interacting particles and that, moving one influences the movement of all the others, then to me it's fine. I think that's perfectly fine. I just didn't understand that as I was reading it. And so the other thing too, this thing here, 10 to the 50, colossal number. I do trust you on this thing where it's with that speed, it will require 10 to the 41 seconds, and all this kind of stuff. I think that's fine. So yeah, I think literally just saying interacting particles and just specifying, explaining what interacting means, I think is perfect. So whatever I said with that paragraph, just ignore what I said in the review and just say that. And I think that would be perfect. And again, I don't know why, but this sentence was not clear to me. I don't know. I cannot explain why, but it was not clear to me when I was reading it. Now reading it, it is clear. But I'm afraid that whatever it was that was unclear to me when I read it the first time might also catch other people up. Once you understand something, looking back at it, it's obvious what was meant. But when you don't understand something clearly, you can't look back in hindsight, So anyway, overall, I think it was quite good. I also quite like the graphic and everything else. I think it looks very good. The videos obviously are way nicer than last time. Like the quality is way higher. And yeah, so I'll take a look at the rest of it one more time, but I don't think there was too much that was changed there. So what I wanted to do was just read through the entire thing one time and make like very minimal edits. And then once I feel like, there's basically no edits left to be done, that's basically good to go. I mean, the editing process just takes time. I'm sorry about that, but I really do appreciate it. Like, genuinely speaking, it's good work. It's really, I think it's really turning out pretty well. So, yeah, thanks a lot for that. Okay, so let's go into io.jl and let's do write to file A. And here's what we're going to do. Back to 4D now. Yeah. So I think what I'm going to do is write to file, and then we need to read in file name A. We're not even in we're not even in a dimension. We're not 1, 2, or 3 dimensions. We're just getting the basic stuff working today. Like literally just an n-body simulator, without any of the spatial splitting, without anything crazy going on, just an n-body simulator, and just kind of building that up and getting everything working. So I guess I'm going to do write to file with an exclamation mark here. And what we're going to do, I think I just do write. So we'll do for I equals 1 to size of A along one dimension, and then we want to do J in the other direction. I didn't. Oh no. Oh no, I think I did 5 spaces. I did. Oh no. Okay, so we want the other dimension here, 2, and we want this to be 4J. Now, I don't know which dimension is which, if I'm being honest. So let's say A is going to be equal to zeros of 310. Okay, then we do size of A, 3 and then 10. So it's going to be, so it will be columns and then rows. Perfect. So I think what I need to do next is I need to flip that. So it's going to be, we're going to do write onto the file name. And then I guess we're going to do, wait, I need to think about this. So we're going to do, we want to do like the element of A that we're working on. And then we want to do, we want the element of A that we're working on. And then we want to do, so it's going to be A of I comma J. Right? Seems fine. And then the question is, do we also do the new tab? And so then the next thing is going to be, it's going to be if J is not equal to size of A2, and then we're going to write a new tab. Oh boy, we're going to have to just check the write function. There's so many things we have to test here. This. So now we also have to create the initialize function. And then once all that is written, we can start testing each individual component just to make sure it works. So we do this, and then we need to do, at the end here, we're going to do write a new line. And we have to write it to the file name. Okay, so then down here, we're also going to do write file name. And then I think we just need, I think we'll do 2 new lines? Or is it just 1 new line? So what I'm trying to do is segment this so I can just plot it easily in GNU plot, like, you know, 1 index at a time. But I don't know. So it's going to be a new line, and then we want a new line. I think it's just 1 new line should do it. But maybe 2 new lines. Let's do 2 new lines just to be safe, because it's going to read it the same. Okay, that should work in principle. So let's go into vigalily.jl, and let's go into include IO. Okay, perfect. So now we have everything ready to go. Let's go to vi simulate.jl. We do output method is equal to file output. Then we're just going to do, what was it? Write file? Write to file with the file name of A. Sure. And here we're going to do write to file. File name. Sure. Okay. And then we're going to do, if the output method is a file name, we want to output the positions at every single point. So it's going to p set dot positions. Sure. And let's just do D4D, D3D, and paste it here. Okay. And add some spaces. Okay, so in principle, this should be outputting the positions at every time step. So we move it forward one step, and then I think, we could have a total time, but I don't think we actually need the total time for this, so I think that's okay. The next thing we have to do is define a file name. It's super messy already, but we'll deal with making it less messy. File name is going to be equal to check.dat or something. I don't know, I just always call it check.dat. That's what we're going to call it. Okay, so we have that done. So the next thing we have to do is the initialize function. Let's go into vi initialization.jl. We're going to create function initialize. And this is just going to take n, which is a number of particles. So I think it was particle number. All right, end here. Literally for now, we're just going to create a random distribution of points. There could be more complicated initialization schemes, but for now, that's all we're going to do. So it's going to be a random distribution in an n-dimensional space. So we need to define essentially our particle struct. So we're going to set it off so that they all have 0 acceleration to begin with, and they all have 0 velocity to begin with. And so you have n-dimensional particles, which is going to be a 2-dimensional grid of size 2n. So it's going to be return particles, and then we're going to do, we probably should also do like grid extents and stuff like that. So we're going to do grid extents is going to be equal to 1 just by default. And so we're going to do particles, and it's going to be rand here. Rand of dimensions should also be read in here. I don't know if I read that in before, but I definitely should have it. Maybe we put it in by default, so it's going to be dims equals 2. So it's going to be rand of dims and then particle number. Do we actually want it that way, or do we want it, we have an XYZ position. In principle, what we're going to want to do is we want which direction is coalesced. So the first direction is coalesced. So probably we want particle number first and then dimensions after that is probably what we want. I would guess, right? So we want particle number first because we're going to want to, we want particle number first and then dimensions because that should be a bit faster. Okay. Okay, and then after that, we're going to multiply this by grid extents. And then subtract 0.5 times grid extents. Okay, the next line, what we're going to do is, oh boy, that is a zeros of particle number, dims, and then zeros for velocities as well, or accelerations. Okay, so it looks like, unfortunately, what we're going to have to do is we're going to have to get the n-body simulator working on the CPU today. And then if we can get that working, I'm going to be pretty happy. And then tomorrow we come back to do the parallelization, the heterogeneous stuff on either CPU or GPU. And then we should be in a good place to start working on Barnes Hut, hopefully by Friday. That would be nice if we could start getting that implemented. Again, parallel Barnes Hut. So this means we should probably go back to the binning problem that we had before with histograms. But we'll get there. We'll get there one step at a time. For now, what I'm going to do is I'm going to take a quick step back because we have the code kind of ready to go. It's now just a matter of kind of testing each little bit, maybe even writing run tests for them. and just kind of going through them. So let's start working on that now. But I'll be right back. Give me 2 minutes, and then we'll get started on that. Thanks, guys, and I'll see you in a bit. Logwire, thank you so much for the follow. Really appreciate it. Yeah, so for those of you guys who may have missed the intro, we've been talking for about, 2.5 hours now. We have about another hour and 20 minutes left in stream. Might end early, but I have a hard deadline for an hour and 20 minutes. I cannot leave after 6 o'clock. That's when I'm leaving today. I just have a dinner date with my wife upstairs. We're doing Taco Tuesday. So yeah, I just can't leave after 6. So that's my hard deadline for today. But we're working on, if you'd believe it, a 4-dimensional galaxy simulation with a couple different goals here. The one big goal that we're working on is just to see like what happens in a 4D galaxy. That's fine. But to do that, we're going to have to do a large number of simulations. So we want the fastest possible n-body simulator, right? And so, it's kind of like the world's fastest galaxy simulator or something like that. If we can get there, that'd be great. Obviously, we have ambitions to get there. So we'll see if we can. But in the overall grand scheme of things, the point of this project is not necessarily to, revolutionize cosmological research or anything. The point here is to use the methods that we learned from the n-body simulations in some computer graphics research later, and then that will eventually work its way back into the physics simulation. So I'm kind of working with two different fields simultaneously. And so this is going to be useful for a bunch of different areas and in different places, blah, blah, blah. So what we're doing right now is just getting the very basic simulation working. So that's just n particles, where n can be any number, all interacting together. We're doing a CPU version today of just that working. And then once we get that working, we'll then move on to the GPU version, or rather heterogeneous version, one that can work on both the CPU and GPU. And then once we have those working, we can then start tackling like more complicated spatial distributions like Barnes Hut and things like this. So right now we're literally just writing everything down and trying to get things to work. So what we've done today, let's just go ahead and do a git diff. We've written, okay, well, let's do, we've written quite a few different files now, and basically what we need to do is just test to make sure all the files work. So that's what I'm going to do right now. So let me do a quick ls here, just run Julia, and we're just going to include io.jl is the first one, because we just wrote that one. Make sure this actually does what we expect it to do. It's write to file. It should take in an array and just write the files to an array. So I'm going to create a is going to be equal to zeros of 3, 10, and then we're just going to write to file, write to file is going to be, the file name is going to be check.dat. And then we're just going to read a, and I'm going to do that a couple times. And now let's go into vi check.dat. Okay, so that didn't work at all. Whatever that file was supposed to do, it didn't work. Let's go vi.io.jl. So this is supposed to go through all of the data in A and write it out. Very cool project. You plan to use smooth particle hydrodynamics or direct n-body simulations for 4D simulation. Right now, our intention is to do direct n-body simulations. I do recognize that smooth particle hydrodynamics will give you slightly better physical results, but my research interest is not so much in the galaxy simulation as it is in the n-body simulator. So I'm mostly interested in making that faster, working on that. But the galaxy simulation is kind of it's a flashy headline just to kind of, first of all, make sure the n-body simulation is working at that scale. That's a very important thing. You want to make sure that it's actually integrating and doing everything well. But secondly, the galaxy simulation allows for me to just do a super large n-body simulation. Like it's just a nice thing to look at as a way for me just to test to make sure that, we understand how to do maybe like regridding and stuff like that at different time scales and all this kind of stuff. Again, if you want a more physically accurate simulation, there are probably going to be more physically accurate simulations out there. What we're looking at doing is basically using the two-dimensional spiral disk galaxy as a test case and trying to optimize that to try to generate that as fast as possible with an n-body simulator. So that's kind of what we're working on right now. As far as smooth particle hydrodynamics, this might be something we look at later, but it's kind of bleeding into fields that I don't really want to touch just yet, and so I didn't really want to go into it in too much detail. Does that mean that if we publish a paper in this area, it's going to be kind of useless? I don't think so. I think people will still find utility in the n-body simulations, which is what we'll be marketing the papers towards. But, it's not going to be so useful for the cosmological community, I don't think. It's more for the numerical or the computational physics community. Okay. Anyway, we're super far from that goal right now. I can't even write to a file. Like that's where we're at right now. It's currently failing. So let me just try to figure out why the write command is failing. I think it's because it should be, let's do write. Hey. Let's do file name. Check.dat. And then we're going to do hey. Okay. So now we're going to do, I think what I need is an exclamation mark here. No. Let's see. So for this, I need to, how do you append it to a file in Julia? Okay, what do we have? Append some data to a file in Julia. Okay. Sure. Oh, I bet you I need to create a... Why would they put an X down here? Like, okay, I get like putting it maybe on the left up here, but the X down here is like the least... Like, should you open the file before writing it? Yeah, in Julia you can write directly with the file name. But yeah, that's what I think. Maybe you're right. Maybe I should do it differently. And I think that's because you need the file IO label. So we're going to say F is going to be equal to open of file name. And then I think if we write to that regularly, I'm not sure if we need, I think it needs to be append mode here, I think is what I need. And then all these guys, when we write to the file name, we just modify that. So it's write to F. And I think you can close the file after, I'm not really sure. But let me try. I think. I don't know. Let's see what happens there. Who cares? All right, let's go ahead and do include. Then we're going to write to file A. Do it a couple times here. Open it up in check.dat. Wonderful. I mean, like, I was not expecting this exactly. I'm not exactly sure what I wrote. Yeah, I really don't know what was written here. We have a tab there. A tab there. What is this? Why do we have a bunch of /200s? All right, let's go ahead and do a remove check.dat. Try it again. Yeah, I don't know what this is that I wrote. So what is A? A is just a bunch of zeros. So I should have gotten a bunch of zeros, but I didn't get a bunch of zeros. I got a bunch of /200s, which I think is like 0.0000. Maybe, okay. Writing numbers to file. Every time. Like, you know, as a physicist, you're like, oh, wow, you have these lofty goals of amazing galaxy simulations. But I is what gets you. Every single time, it's like, how do I write to file? Like, you know, that's just the story of my life, you know? 128? Interesting. Why is it 128? This is why I usually use delimited files. But obviously that didn't work. Oh, maybe I have to specifically turn it into string. Yeah, let's do Barnes Hut. Yeah, 1 second. Let's go into vi.io and let's modify this specifically and turn it into a string. Let's do string here, there. The tabs I think were working and the new lines I think were working. So let's go ahead and include it again. Now let's do write to file and let's go into check.dat. There we go, got it working, perfect. Let's go ahead and remove check.dat. I think it was working fine. Let's just do it a couple more times. And then we look at check.dat. Sure. Okay, this looks great to me. Wonderful. All right, great. So let's try to initialize some particles and output that. Does CUDA.jl already abstract multiple GPUs, or do you have to write additional code to use multiple GPUs? That's a very good question. The answer is that CUDA.jl, similar to CUDA, itself does not already abstract to multiple GPUs. You always have to do the inter-GPU communication. There are some things that you could do that will do the inter-GPU communication for you, like ArrayFire or something like that. But the truth is, in general, if you're going to do distributed GPU computation, you kind of want to do that you're on your own. Like you want to manually pass those messages back and forth, just because that is the slowest part of your process, and you want to make sure you're minimizing that computation. And I just wouldn't trust an algorithm to do that more efficiently than I could. Is my short answer there. Now, there's probably better ways to do it. Like, you know, for example, I would probably trust, you know, kernel abstractions to do it correctly if it ever works. But right now it's just not built into the ecosystem. And now, look, there could have been advancements in the last 5 to 10 years that I've missed. I haven't really been keeping like super up to date. But as far as I'm aware, there is no, like CUDA does not currently allow you to do inter-GPU communications. Well, okay, you kind of can with like the FFT wrappers and stuff like that, but it's kind of all, you kind of want to do it yourself, usually, is the actual answer there. Now, maybe, you know, maybe you're like an expert in GPU computing and you know more than I do. I mean, again, my PhD was 2 years ago. I do primarily GPU computing, and I have been doing primarily GPU computing for like 6 years. But there could be still stuff I don't know. So anyway, let's go back. So that seemed to work okay. So the next file I'm going to do is include ls here. Sorry. Let me go into vi, and we're going to do galilee.jl. And the next thing I want to do is include particles. dt here, parti.jl. This here, dd there, write and quit. Okay, so now I'm going to go ahead and read the particles in and see if that works. So we're going to include particles.jl. Oh, it's just particle.jl. Well, let me modify the name really quick to be particles plural. Move particles with an S. Let's go into vi particles.jl. Struct particles should be fine. Okay, let's go ahead and try it out. So we're going to include particles.jl. CURA, not defined. That's because we haven't used CUDA yet. So let's do using CUDA. And then we'll read instruct particles. We're going to initialize those particles, and then we're going to try to write those initialized particles to a file. So we're going to include particles.jl. Seems fine. So let's go in, take a look at what is it? Try to take a look at the initialize function. So initialization.jl. Oops, sorry. vi initialization.jl. So all this does is return particles here with a certain particle number of dimensions 2 right now in the grid extents. So let's give it a go. So we're going to do... What am I going to do? Give me 1 second. I need to think about this. So I want to do include... it should be initialization.jl. Okay, so we have initialize. So we should be able to do p set is going to be equal to initialize of 10. Wonderful. Perfect. Great. All right, let's try it again. So it doesn't like the dot minus for some reason. Let's try including it one more time and do this guy. Okay, so that time it worked, which is great. So let me check the initialization.jl function one more time. I don't like doing this, but I'm gonna do that. All right, perfect. Okay, so the next thing is we have the p set now. Let's do p set.positions here. So we have that defined. And so now what I want to do is just write that out to file multiple times and see what happens. So we're going to do write to file, check.dat, and we're going to do pset dot positions. Okay, do that a couple times, and now we're going to take a look at check.dat. Perfect, seems to be just fine. So let's go ahead and do remove check.dat. Good, we're slowly getting there. So now for the actual real stuff that we need to test. So all this initialization stuff, I mean, we should probably check that, but this is all stuff that isn't going to necessarily fail. This upcoming stuff that we're going to test will almost certainly fail. So let's go ahead and take a look at what we have. So ls here, ls here. So we have the initialization.jl, we have the io.jl, which are the two that we tested. Now we have to test forces.jl and simulate.jl. So let me go into include. This one might break. Forces.jl. It ran, which is fine. Now we're also going to include simulate.jl. Okay, unexpected equal sign. Let's go into that one on line 12. Equal sign is here. If output method is equal to... Oh, I thought I could do that. Oh, it's double equals. That's why. I'm an idiot. Okay, perfect. I was sitting there. I was like, oh no. Oh, I have no idea what to do. It's like, I'm just dumb. Let's try it again. Okay, so we now have the run function. Let's go into VI simulate one more time. Okay, so the next thing I want to do here is I want to have the dimensions also defined here. Dims is going to be equal to 2. And then in here, we're going to read in dims... dims equal 2. Equal dims or something. That should do it. So I guess I'm just going to try to run it and see what happens, right? Like, what's the worst that could happen, right? It breaks. You know, I've been broken my entire life. Okay, so we're going to do just run, I guess. Right? Run. Now, what do we actually need here? So we need particle number, time step, and then iterations. So we're going to do run. We'll do 10. We're going to do time steps. It's going to be 1, 10. Yeah. Okay, so let's go into vi forces.jl. I called it find x instead of find acceleration. I'm going to move the optional arguments down to the next line. All right, let's re-include that guy. There we go. Try it one more time. Okay, find accelerations, plural. Okay, there we go. Not a problem. Let's keep going. Include run. Objects of type symbol are not callable. I thought you could just directly call the functions that way. Maybe... okay, maybe I just need to not have them symbols. Okay, that's fine. Let's go into vi forces.jl. So what do we have here? I think if I just don't have them as symbols, everything's going to work just fine. So we can just do gravity, and that's just going to naturally be a function pointer. I don't really like that, but that's fine. Calculation is true, Verlet, gravity. Up here, we have end body and gravity. All right, quit. Let's go into vi simulate.jl, and we're just going to modify all these guys. So gravity, end body, integrator, file output here, and then there. Perfect. So now we're going to re-include both those guys. Forces include simulate.jl, missing comma, line 4. Line 4. This is going to be, where is it? Dims equals 2 there. There we go. And now we're going to do run again and see what happens. Okay, end body not defined. It's a function, which might be why it's not defined. I don't like passing these functions in this way, by the way. Let me do something different. So I'm going to run this over here. You really chose your time to add, to not add a push-up count, push-up per error. To be fair, I should probably be doing that more. I'm probably going to add it back to like tomorrow's stream or something like that. It's just that recently, like, you know, one of the main reasons I added the Swole Leos workout routine to begin with was just because I was, ooh, that's bright. Is that better lighting? I don't think so. I think it's too yellow. Anyway, the reason I added the Swole Leos workout routine is because I was just super tired all the time. And recently I haven't been as tired, so I haven't felt the need to re-implement the Swole Leos routine. But I might add it back in. I probably should add it back in actually soon. It's just, I haven't been too green, maybe. So what these are like little lights that, so, okay, this is hard to describe. Let me explain. All right, let me go into Ramble Leos mode for 2 seconds and let me explain what this is. Here's my Ramble Leos mode. Perfect. Okay, right, so what are these? So these things, hello, hey, how you doing? Okay, so these guys right here are like lights that I can press this button and they'll turn on, right? You might be asking, okay, but what are these useful for? So here's what they're useful for. My entire computer, let me see if I can do this right. So my entire computer is in a carry-on computer case, right? So I have a video on this, but here's my computer. I'm trying to make it so it's not too nauseating, but there's my computer right there, right? So there's chat right over there. This is my computer. And what I can do is I can actually slot this guy. I'm sorry for the shaky cam. I can slot this guy right in here. Wait, can I just put this here maybe? Yeah, okay, you can see it there. I can slot this guy right in here. And it sits there via Velcro. And then what you do is just turn it on just before stream. And then I have a built-in light if I need it. So let me move this back over here. Oh, wait, so here it is with the light on, right there. But I also have that lamp, and I also have that lamp, and I also got the monitor over here. So, like, it's kind of not super necessary, but I used it a lot in Okinawa. And so then I just put it back. This maybe? Is that okay? Maybe I need to move it up a little bit. Sure. Okay. That almost. Oh no! Everything's completely broken right now. Let me. One more second. There. Yeah. Okay. So here's it with the light on, and here's it with the light off. It doesn't really change too much. I can leave it on or off, but it was super useful in Okinawa. They let you on that. They let you with that case in the airplane. Yeah, definitely. I brought it on like multiple flights actually. I brought it on flights in the U.S. internationally between countries. So I brought it on a flight interstate to get to a flight to Japan. So I flew to Japan, I flew to France, I flew to Spain. I've flown all over the place. It's fine. Like so far, no one said anything about it. Like we almost got caught up once, but then I just explained it was a computer and they were like, it's fine. They only care about like water and stuff. They don't care about like, carry on computers or anything like that. So I was actually surprised that I was allowed to bring it on. Like I was actually genuinely thinking that they were going to take it from me. And I was like, what are we going to do? Because like this computer is worth like $2,500, probably more actually. So if they take it from me, I'm like in a lot of pain, but it was super useful when I was moving because it saved an entire suitcase. So we could bring an entirely new suitcase with us that we couldn't have before, as long as it's not water cooled. Right. So there is no liquid in it. It's all air cooled. And I made that for the explicit purpose of not dealing with the TSA. So, what am I doing over here? Control C. Oh, wait. Control D. Control D. Okay, so we're in Galilee, CD to source. L is here. Let's run Julia. And I'm just going to work on everything in the left terminal and have the code up on the right terminal. So we're going to include, just include everything. So we're going to start by including, can we just include Galilee? Maybe we can. Galilee.jl. That should include everything. Hopefully it works. And then once we have that included, we should be good to go. As long as it's not water cooled. Yeah, let me get some water. So I'm a big fan of this computer, by the way. Like, it's just, aesthetically speaking, it is the coolest computer. Like, I just cannot imagine a better looking computer. I'm just like a huge fan of it. Like, all around, it's just amazing. Like, okay, so let's just go ahead and do run of 10.1.10. Okay, so let's just figure it out. Maybe I need to do Galilee.run of 10.1.10. Sure, okay. So end body not defined. Let's go there and let's figure it out. There should be a Galilee.endBody. Oh, it's endBody exclamation mark. That explains it. VI simulate.jl. Sure. And it's just endBody exclamation mark, which maybe isn't the best, but let's go here. Okay, also let's add a space. I have not been consistent with my spacing at all. That's okay. Okay, write that. Perfect. We're going to re-include Galilee.jl, see if it works. And now we should be able to just Galilee.run. Where are you? .run of 10.1.10. File output not defined. Perfect. Output method is equal to file output. Okay, sure. So this is where I actually do want one of these guys. Okay, so we're going to re-include Galilee again. Try running it one more time. Okay, endBody not defined. That is because... Why? This is going to be on line forces.jl3. So we're actually in another file, 3. Sim type is going to be endBody exclamation mark. There. Right and quit. And actually probably for the find acceleration in here, we probably want to read in a bunch of different optional arguments. So we probably want to read in... Oh, Toby for Prime, thank you so much for following. Sorry, I missed that a few minutes ago. We're going to do probably force law is equal to force law sim type is equal to sim type. What else do we want here? I'm going to move it down to the next line. We want integrator. Oh, we don't need the integrator yet. That's fine. So integrator, output methods, that's it. Right here, go over here, include it one more time. And then we're going to run Galilee.run. Okay, seem to do something. Particles not defined. That's perfect. What line is that on? That's going to be on line forces 11. Here. For ion length particles, that's because it should be positions. Right, quit. Over here, we're going to do include again, Galilee.run. Particles not defined. What? 13. Oh, I'm just an idiot. That's what I am. All right, run again, Galilee.run. Okay, no method matching Verlet for Galilei dot particles. Okay, perfect. So this is where we need to, basically we need to split this up. So what we need to do is we need to, if we're running with Verlet integration requires knowing knowledge of the previous time step. I think most things probably require having some knowledge of the previous time step. So this is where I thought we were going to get caught up a bit. So we're trying to move all the particles forward a single time step. And to do that, we need to know what it was before. So what we're going to do is we are going to, where do we call Verlet? We're going to create a function for Verlet, which is going to take in p set of particles here. Okay, so this is the issue. Let's go ahead and end here, write and quit, and let's go into simulate. So what this means is we got through the find acceleration step. And not entirely sure the find acceleration step was working, but we got through that step. We're on the next step here for the integrator, which is going to be integrating pset, which is going to have a set of accelerations and a set of previous points and everything. So I'm wondering, I'm wondering what the best thing to do here would be. What you need is an FPGA card inside your computer, then it would be complete. Wait, why do we need the FPGA card? To be fair, like, FPGAs are quite cool, but I haven't really found an actual use for them yet. I mean, like, I know they're probably pretty good at sparse computation and stuff like that, but like every time I think about using one, it's like I haven't seen a need for it yet. So if you can give me a compelling application for FPGAs plural, I would be into that. Just let me know what it is. Okay. So what do we have now? We have find accelerations of pset. So that worked. Now we have integrator of pset. What I might do is I might just... So what this is going to do is it's going to... Maybe I just read in pset twice. So it says that the... Okay. I might do pset1, pset2. That might be what I do. I might create a pset2 and I might just read that in and I might just do it that way. And that might be what we do. So we might do yank paste here, because what's going to happen in the Verlet integration here is we're going to read in both of them, and then I'm going to be basically cycling through. I'm going to be cycling through. Wait a minute. So the previous position. Wait. We have the position one. We only need the previous positions, I think. Right, we only need the previous positions. That's fine. That's fine. Let's just do it this way. The simulate.jl, pset2 is what I'm going to call it. And then here we're going to do pset and then pset2. Right, this, go over here, we're going to include it again. Then we're going to run galilei.run. Okay, no method matching Verlet galilei.particles, galilei.particles. Okay, what do I actually have then? I think I just called them of type particles, but they should be of type Galilei.particles, which is interesting as to why that distinction is being made. D3D. So maybe what I need to do is export particles to begin with. Let's do Control D and run back a directory and do Julia --project. Okay, now we're using Galilei here. Galilei does not have CUDA in its dependencies. Oh, it doesn't have CUDA. Okay, that's fine. We'll fix that in just a second. That's a little things to do. Let's go to add CUDA. I'm surprised it doesn't have CUDA. I must have really screwed up when I was creating the manifest here. So we probably also have to create CUDA kernels then. Interesting. Why? I remember adding this yesterday. I don't remember this problem. Anyway, I'm hoping we get something. Like just anything working, and then tomorrow we can work on making sure it's like actually working correctly. But like I just want something running, something that I can commit and be like, we did it. You know, that's what I'm looking for. Yeah, but actually, in truth, we've done a lot of work today, right? Like if we just do a what is it, WC of star? What is that? The word count. We've added, you know, can you see WC dot? Okay, I don't know. We've added a bunch of lines of code today, like a couple hundred, 200, maybe 150, I don't know. Got a lot of work done. I'm relatively happy with where we are. Add CUDA kernels. My wife upstairs said it's like a typhoon outside. You can probably hear it. It's like on the windows. I'm sorry about that. Hello, I've not heard of Julia yet. So Julia is a programming language that is just as fast as C or Fortran or any of the languages that you know for speed and computation and scientific computing, but it's relatively easy to write. I would argue even easier to write than Python. I use it predominantly for general purpose GPU computing, which is why I really like it, but other people like it for other reasons. So that's the language that I primarily use. I have been using for years, big fan of it. And I mean, I've done some Julia development for like kernel abstractions and stuff, which is a heterogeneous computing library that allows for you to write a single piece of code that executes on multiple different pieces of hardware. I don't know exactly, but some cellular automata algorithms can be more efficiently implemented inside FPGA. The CAM machine was implemented in FPGA-like hardware. Right, so actually we had some idea way back, like during my PhD. My advisor was trying to find some utility in FPGAs, and he was like, oh, we could do split operator method in FPGAs. And I was like, why though? Like, what is the utility in using an FPGA here? And there wasn't really any. And the fact is, it might be an interesting area of research for some people. Like, yeah, like N-body and FPGA, I'm sure people do this, right? But right now there just isn't the hardware in the HPC space to, right. So the high performance computers are by and large moving towards the GPUs. They're not moving towards FPGAs. You have to fundamentally rewrite your code base to work on GPUs, but if you're used to distributed computing, parallel computing, kind of the same thing. FPGAs, though, are just so fundamentally different that you have to rethink pretty much everything when you put it on an FPGA. And so they didn't really catch on. In the same way that GPUs didn't catch on until CUDA existed, you know? You need something like easy for scientists to use, and right now there just isn't that. Intel is pushing for FPGAs. Could be true, and in the next few years, you know, maybe we'll see everyone shifting towards FPGAs. I love actually seeing new architectures, like, you know, giving me new tools to work on, quantum computing being kind of a new paradigm that people are working on right now. I think it's super cool. I love seeing that. And I would love to work on that in the future, but right now, I'm not seeing the need to invest in it, predominantly because, you know, like I said before, I'm currently trying to do this open research lab, and there's some of that, in order to get that to work, some of that needs to be catchy. It needs to be flashy. And, you know, doing quantum simulations on FPGAs, it's flashy from the academic side, but from the, you know, general usability side, you know, unless there's something fundamentally new that you can do with FPGAs that allow you to do simulations faster, like, you know, a bigger simulation, a type of this, a type of that you couldn't do before, I'm not really seeing the need to invest yet. I'm not saying there isn't a need to invest. I'm just saying right now I'm not seeing it. So that's kind of where I'm at with that. I know it's kind of a bit, that's a cop-out answer, but I'm cautiously optimistic that there will be something in the near future that allows me to use FPGAs, and I'm really hoping that happens. But I'm not going to jump into it until I know there's reason to jump into it, right? Anyway, that's kind of wishy-washy. Sorry about that. Let me look for particles. No, it's not there. So I think what I need to do is specifically export particles. So let's go into vi particles.jl, and we're going to do export particles. Okay, let me just try rereading in Galilee. So we're going to do here, we're going to do Julia _ project using revise, and now using Galilee. And then hopefully things are just going to work. Doesn't have kernel abstractions in this dependency. Oh my gosh, what am I doing? How am I so bad at dependencies in Julia? Are you kidding me? Add kernel abstractions. My gosh, getting there, but man, I'm slow. Okay, we'll add kernel abstractions in there. Okay, we have that added in, perfect. Now let me just see if I have particle. Okay, good, I have particles defined. So I think I should be able to do Galilee.run of 10.1.10. Method error, no method matching relay of particles. Right, perfect. So we're gonna do, what am I doing here? I'm gonna do Chautomate sumimasen. Simulate. And then here we're gonna do pset1, pset2, and we wanna specifically read in DT. Try running it one more time. One API from Intel is trying to solve that problem, but I don't know if you can test that now, as there's no consumer available FPGA hardware except some hobby scene boards, which are very slow. Yeah, so that's also the other thing, right? What did I call it? Time step. Oh, look, everyone calls it DT. I'm just gonna call it DT. Screw it. No method matching for lay particles. Okay. No method matching for lay float 64. What is this? Closing candidates are any. All right, what do we have here? P-set 1, acceleration. I'm missing a DT, and that's because this guy for that needs a DT in it. Okay, given a particle has no field of velocities. What does it have? I misspelled velocities? Okay, we're gonna have to do that one more time. All right, using revise. Oh, I think we're actually making progress here, guys. Like, I'm actually cautiously optimistic. Come on, babe. You know what you want to do. All right, let me get some water. All right, let's try Galilei.run. Oh, man. Okay, velocity 1 not defined. Totally fine. We got forces.jl val1. What is it called? Val1. Oh, this is just going to be particles.velocity. Sorry, pset 1 dot velocities is equal to that. And then we also want to do the same thing here. Oop. But it's pset 2. Okay, so here we're going to run it one more time. We're slowly working our way through it, like one step at a time. We have something that seems to be running. It ran. Okay. Come on. ls dot check dot dat. We have particles. They are identical, but we have particles now. Here, remove check dot dat. Try it one more time. Galilei.run. Go over here. Take a look at check dot dat. I'm not convinced that anything is happening, but I'm convinced we have something being output. Julia is slow. Julia is quite quick. I mean, if you have justification for saying why Julia is slow, I mean, feel free to let me know. But so far as I'm aware, and from the benchmarks I've seen, I mean, I worked with Julia on like some of the fastest supercomputers, the fastest supercomputer in existence, at the time, not now, but a few years ago. I don't think anything can beat it in raw throughput except for C++ with some loads, and Fortran also with some loads. I think it hits basically peak petaflops. It's just a joke on why we're working slowly. Oh, fair enough. You still have your README. That's because I'm on a different branch. I'll rebase onto master in just a second. I switched. I needed to. Yeah, I need to fix that. Yep. But if I rebase onto master, it should be fine. Main. Not gonna do it now. We're gonna do it later. I'm gonna commit everything and we'll do it later. VI, what do we want here? In fact, maybe this is a good time. Everything seems to be running. We have a simple test case. Let me do, let's actually have this now. Git add dot, git status. We want to, should we want to add git add project.toml? Sure. Untracked files, those should be fine. Manifest, check.dat, tests, that should all be fine. Perfect. Okay, so git commit -m and just saying it runs, but might have errors. A simple skeleton. I guess Let's just say simple skeleton. Okay, that's what I'm gonna write down. Okay, so we're gonna go here. Now we're gonna get rebase master main. Okay, there we go. So I'm gonna do ls back directory. So now, okay. Get status readme.m comma d. Get status dot. What? Get remove readme.m comma d. What? What? Okay. Let me check the main branch. Just get commit dash m. Removing unnecessary readme file. All right. Get checkout main ls here. I don't know what happened there. Get checkout. Sure, that'll work. If we had particles, right. Check to see if it was accidentally sending CERN. No, you're definitely not. I'm very far from that. Julia, it would be great if you can do static compilation and create an executable, but that is the next milestone. It seems many core developers want that feature. I 100% agree with you there. It was just not deleted during the rebase. Yeah, I don't know exactly what happened there. But yeah, so as far as building an executable is concerned, I am 100% on board with that. Like, we need to be able to build an executable, and without that, you're right, Julia just will not, like, look, it's fine. Like, it's fine for HPC, whatever. But I mean, it really isn't. Like, building an executable, even if it isn't like a, build once, run anywhere type of thing, just building a single executable is incredibly important. And you can do that for most Julia code, but once you start using exotic hardware, like on GPUs and stuff like that, I don't know, it's not particularly good. Is this Rambling Laos? No, we're not on Ramble Laos yet. If you want, we were just on Ramble Laos. We can come back later. We're working slowly, Laos. That would help us greatly with the algorithm archive. Yeah, I mean, yeah. But there's only so much you can do. I mean, like, look, the truth is, I talk to a lot of the core developers, and the problem is the following, right? They don't see this as a problem because people are not talking to them about the problem. But the reason people aren't talking to them about the problem is all the people who saw it as a problem are not using Julia, right? They're using other languages, right? So it's like what is that problem when, like, what is the problem, like, something bias? It's like survivorship bias, I think, is the one that we're looking at, where, like, the only people that are going to give you feedback on your product are those who are actually using your product, but everyone else has already left. Like, that's the like main issue with, like, like, core developers are like, well, the people aren't even like, the people who are using our code base are not actually, like, doing this thing. It's like, well, yeah, because all the people who wanted to do that thing are doing something else now. It's just that happens all the time, not only with, like, code development, just a bunch of different things. Okay, so we have this running. Let me run GNU plot. Okay, here's what I'm going to do. I'm going to do plot check.dat. Okay, that's the first, and we're going to do I0. Now let's do I10, and we're going to do replot. Okay, I was not expecting. Oh, probably I9 is what I need. So they're the exact same points, which means our force integration scheme is definitely not working. And it's probably because our struct particle is not mutable. We probably want to make sure it is a mutable struct. So let's go here and let's fix that. Particles. Let's change this to a mutable struct. Right, this, go over here, Control D, Julia. Try running it using revise, and then using Galilee. Try running it again. And hopefully we see 3 dramatically different time steps. That's what we're looking for. Like we see the particles kind of clumping together. That's what we want. We want something. I don't know what exactly, but we want the particles to move. So we're going to go to Galilee.run. And I think I also need to remove. What I want to do is do vi simulate source simulate.jl. Yeah, let me just remove the check.dat file. Okay, let's run it one more time. Hopefully we get something. Let's go into vi check.dat. Nah, it's still the same point. They're all the same. 0.456, 0.45607. Yeah, okay. So we're not evolving with time, which is fine. Julie doesn't throw an error. Why you try to mutate non-mutable struct? What it does instead makes a copy. I don't know. I thought the mutableness was it, but it might not be it. It reminds me of some schoolwork on how to optimize the hell out of it. Yeah, that's actually what we're working on right now. N-body simulations are like definitely they're like endlessly optimizable. There's a lot of problems like that are just endlessly optimizable. And so that's why we're actually looking at this, because we think there's some cross-pollination here between, or I think there's cross-pollination here between the computer graphics literature that do basically similar problems in color quantization and the obviously N-body galaxy simulations and stuff like that. But there's also, I think, there's pollination both ways. I think the time dependentness of N-body simulations can help with like color quantized video, which is something that we need for like our ASCII art generation and stuff. But I also think it goes the other way around, where I think we can use our knowledge of how to spatially distribute things appropriately with color quantization in the N-body simulations as well. So we're just gonna see what we can do. I mean, like, I would like to be able to say, oh, we have the world's fastest galaxy simulation running in parallel on the GPU. Like, that's where I want to get to, but obviously, we're gonna fall short of that. The question is, how far short do we fall? I don't know. We'll just see what happens. So we are currently not able to evolve any particles in space. So right now, we are very far from where we need to be. So what are we going to do next? LS here. Let's just go into CD source and go into vi forces.jl. Let's go here and let's remove check.dat. And let's think about what's happening here. So you're right that Julia should probably give us an error if you're mutating an immutable struct or something, but it doesn't. I don't think it does anyway. So we have N-body focusing on the accelerations. So I guess the first thing we need to do is check to see if the accelerations are actually being output correctly. You have two Verlet functions? Yeah, I do. So one is calling, acting on the set of particles, and then we're using dynamic dispatch so that we also have another one calling this one. So the idea is that you call one as a user, and then the other one's the actual underlying algorithm, like the simplest form. So that's actually intended. Okay, so we're going to go into VI. Are you sure the correct one is being called? Yeah, I'm entirely sure. You can't call the other one. It's not possible. It has the wrong arguments. I mean, yeah, and even if the other one was being called, it'd still be fine. Okay, so let's go into vi simulate.jl. And let me go ahead and check to see the accelerations here. So we found the accelerations. What I want to do is write to a new file. And here we're just going to call it accelerations, whatever. .dat. And let's just make sure that we're actually writing something here. So we're going to do getly.run. It's doing some pre-compilation stuff, I guess. Let's go here, ls, and we should have an accelerate.dat. So let's go there, vi accelerations.dat. Okay, so we do have accelerations, which is fine. Good. So it looks like we should be moving. So we know that that's being generated. So let's go ahead and remove accelerations.dat. Okay, so we have that being run. Again, guys, just for the record, I only have about 30 minutes left of stream today. Ordinarily, I would do a bit of a longer stream if I could, but today we're doing a hard cutoff at 6 because I'm doing Taco Tuesday with my wife upstairs, and it's just something it's one day a week that we make sure that we sit down together, we eat dinner, and all that kind of stuff. So I'm not missing that no matter what. So 30 minutes, that's where we're at, and then we'll come back tomorrow to do more stuff. So just letting everyone know, only 30 minutes left in stream. If there's somebody that you want to raid at the end of stream, feel free to let me know, and I might or might not do the raid. It depends on how I'm feeling, and like how much time is left before 6, because I gotta go raid at 6, which is in 30 minutes. Yeah, talks with the wife. Visa stuff done. The Visa stuff. So here's what happened with that. So we just decided the reason the Visa stuff was kind of a problem was because we wanted to go back to the US for our winter holidays, and we just decided, okay, look, I mean, if there's a chance that the Visa stuff is going to run into problems, we're just not going to go back for winter. We're just going to stay here. So the visa stuff is done in that we have decided not to poke the bear or poke the lion or whatever there. So let's go into VI forces.jl. I'm not entirely sure what we're doing, but something might be broken here. So what happens is we call Verlet here, which takes a particle set 1, a particle set 2, and a DT. So more streams in. Yeah, I think it's actually probably pretty good. I mean, I am genuinely trying to do like more longer streams on Twitch. Like I'm trying to make this be basically not my entire workday, but half my workday on Twitch. Because there's a lot of stuff I can't show, like, or can't easily show. Like going through papers is just so much faster off of Twitch than it is on Twitch. And yeah, every time I try to do like paper streams on Twitch, like some people are into it, but you know, I can't do that every day. And so even though I read like, 3 or 4 papers a day, I can't just show that on Twitch. So there's stuff like that I have to do off stream. A bunch of other stuff I have to do off stream, like more of the theoretical stuff, like figuring out how this works with that, what we could do here, all this kind of stuff. So basically the planning, all that stuff does have to happen off of Twitch. But like stuff like this, just writing a Barnes Hut simulator and stuff, easy to do on stream. And so it kind of depends on how we go here. I think everything is faster out of Twitch. That's not always true. It depends on like a certain number of things. Like sometimes writing code on Twitch is actually way faster because, there's 2 things. One is, sure, on Twitch, I'm constantly distracted by chat. But when I'm not on Twitch, I'm constantly distracted by everything else, And the question is chat more distracting than like the archive or like, other things? It's probably equally as distracting as everything else in life. More than that, chat actually gives pretty good advice a lot of the times. Like sometimes I'll be like, hey, how do I do this? And people are like, oh yeah, that's maybe you do it this way. I'm like, oh, great. Like there's actually a back and forth there that's quite useful. So some things are definitely more efficient off of stream, but I don't think the stuff that I do on stream, like the code development stuff, is necessarily inefficient because I'm streaming it, In some rare moments, sometimes chat helps. But the thing is, when you're debugging, right, and you're just lost in a sea of error messages and you have no idea what's happening, like any forward movement is helpful there. So even people who are just like, oh, what about this? What about this? And me just kind of talking that through and seeing if that's actually a problem, even if I'm like, no, that's not a problem. Like, and I sound really gruff about it. Like those comments are super helpful because it allows me to think or maybe start tackling a problem from a different perspective. Or the fact that chat's here means that sometimes I'll take a step back and I'll be like, okay, so what are we doing? Why are we doing that? And it helps 2 ways. One, it helps give, kind of a perspective to you guys, so you now understand where the error is coming from, but it also helps me kind of work through the code and make sure that there's nothing broken, So all of this kind of like, rubber duck debugging, all this kind of stuff, it's super helpful. Plus, sometimes you're just tired in the middle of programming, and sometimes you just want to talk to someone for a few minutes before getting back to it, or you need your mind to wander a little bit, and that's super helpful as well. So I don't know, I think it's about equally as inefficient. I don't think any programmer is like actually truly efficient. I think there's just like levels of inefficiency, So we have temporary position is equal to position 1. We say position 1 is equal to that. And then we say position 2 is equal to that. Okay, seems fine to me. So up here, I should probably have these be exclamation marks as well. Let me go ahead and change the notation while we're thinking about this. So this is exclamation mark. Oh, so this is an exclamation mark because we are mutating the data. It's just notational. I did it again. It's just notational. It doesn't matter. So we do this here. I'm going to change this so it's also an exclamation mark there. And then we do this as well. What my fear is that maybe we're running into an issue with the unrolling of the for loop. So let's go here, or the broadcasting operation. I'm not entirely sure why that would be the case, but maybe that is the case. So let's also go into VI simulate.jl and modify this so the default integrator is Verlet. Okay, let's go there. You know what the problem is? The previous position is the same now. That's the problem. Right, okay, yeah, that's obviously the problem. The previous position is the same as the current position. That's why we're running into this issue. So we can't properly simulate the movement of the particles, because all we have is a position and an acceleration. So we read in pset and pset 2. So these guys should change. pset and pset2 should change with time. Maybe? Forces.jl. So we have relay here. It reads in position 1. So we have relay here. It reads in the position pset1.accelerations, positions, pset2.positions, pset1.accelerations, pset2.accelerations. Then if we want to calculate the velocity, we can, but that's not essential. So down here we say the temporary position is position 1. Then we say position 1 is going to be equal to position 1 times 2 minus position 2 plus some sort of acceleration. And then we modify position 2 to be what the temp position was before, and we change the acceleration. So we've changed the current position, the previous position, and the acceleration. So let me just try something. I don't think this is a problem, but I'm just double checking. For I is equal to 1 to size of pset1 dot positions of 2, I believe is what I want. And here, and now I'm just going to do yank to yank. And we're going to paste it up here. This allows me to do some more debugging as well. Okay, let me go ahead and comment these lines out for now. There and here. And now in here what we're going to do is positions of I, and we're just going to put an I in all of these guys. Okay, so we have all these. What I'm going to do is I'm actually going to print out pset1, 1 second, 1 dot positions of I, and then we're also going to print it out afterwards. So print line here, yank and paste. I misspelled print line. Let me fix that. There and there. Perfect. So let's try it one more time. Okay, so what exactly was I intending to get there? Let me think about this. So, okay, this is actually fine. This is fine. So we're seeing that going in and out of this relay integration thing is actually not working. Let me try this one more time here. Run it one more time. Okay, right. So there is no difference between this one and that one. Absolutely no difference. So this means that there's absolutely something wrong with our relay integration. Yes. So with this line, there's something wrong with this. So what should be happening is we have 4i size. So we're going through all of our particles. Let me also check something else really quick. Let me remove these print lines. Let me remove that. And let me also remove this. Because we should be doing 100 time steps, right? So we should be doing 10 time steps. So we should be outputting 100. Let me just print something. Print line. Pset1 dot positions of 2 here, and we're going to do Galilei.run. What happened there? It must be that. No. This is what I need. Okay, that was not what I was expecting to be printed out at all, honestly. I genuinely thought, this is because it should be size. Okay, it says 2. I think I wanted 1 here. That might have been why we screwed up so badly. Galilei.run. Okay. Yeah, so let's try this again. So DD here, X here, X here. Write this, go over here. Try it one more time. Okay, so here what we should see is, yeah, so this is the number of particles we wanted. But what I was hoping to see is we run pset1.positions, then we modify pset1.positions of I. So we change what that is, and then we should see a different one before and after, but we are not seeing that. So what I'm going to do next is I'm going to create a particle set, particles, whatever, of just do 1s of 10, 0s of 10, 0s of 10 or something. Perfect. Now we do particles, P is going to be equal to that. Okay, so now I'm going to say P dot positions of 1 is equal to that, equals 2. Sorry, equals 2. That seems fine. So now if I do P dot positions of 1. Okay, so we can definitely set them differently, which is fine. I don't understand the problem then. So let me just try running Verlet. So Galilei dot Verlet on. Oh, I guess it's going to be, we can just read in different positions. So let's do 1, 2, 3, 4, 1. Why not? What's wrong with that? Maybe they have to be all floats? That's fine. Oh, it's an exclamation mark. That's what we need. Oh, that was not an exclamation mark. Let me try it one more time. 3. It's because they're not arrays. Okay, that's fine. Oh, is that the problem? I see. Okay, I think I see the problem now. Right. I wanted to mutate the data, but the issue is that I can't do that. Okay, I see what happened. The issue here is this. This dot needs to be removed. I think that'll work just fine. Yep. Let's go over here, remove check.dat. Try running it one more time. Okay, so now let's take a look at check.dat. Is it changing? No, they're still the same particles. Dang it. I thought I had it. Okay, so let me try running it one more time. What I might do is I might move this so that you guys can see it a bit better. So let me make this huge. Move it up here, and I'll just switch between these two terminals. I know it's a bit messy, but it is what it is. And again, I've only got another 20 minutes left in stream today, so I'm hoping we can get something done. Let's go into viforces.jl. So what I tried to do is grab 2 particle sets. So we should have P here, and I should be able to run Galilee dot Verlet exclamation mark of P dot positions P dot positions P dot positions P dot positions. And what's the issue? Oh, I need a DT. 1. Okay, what does that do? We are getting the same value out. Now the question is that what we're supposed to get? So here what we're going to do is it's going to be 2 times, where is it? So what we should be seeing here is that it's 2, try to change DT to 10. No, that did nothing. It should be, is that because this is supposed to be copy? That did nothing. Let's go into vi check.dat. Now it's the same data file. Remove check.dat. Try running it one more time. Open it up. Try running it one more time. Open it up. Yeah, okay, it's the same. Crap. Okay, so for some reason, our Verlet integration function is not modifying our positions at all. That's our issue here. So when we run this, it's not actually changing anything. So what we're doing is we're reading in. Is this because we're doing a bunch of copies here instead? So maybe if I do. So this is going to be equal to temp position. And maybe what I should be doing is copy. Maybe I'm just like getting all the pointers mixed up. G385, no. Let me try it one more time. So right here, obviously the issue is that we have p dot positions. Okay, here's what I'm gonna do. I'm gonna create a new particle set. P is gonna equal to this, and it's just gonna be ones, 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 ones. So we're gonna have a bunch of ones. Okay, now up here, when we define the different, let me go here to visimulate.jl. pset1, we have 2 separate initializations. So actually, p set 2, it doesn't even matter. Okay, so p, and now let's do, sure. So we have p, and we're going to say p2 is going to be equal to that. So now what I'm going to do is just run Galilee.Verlet here, and we're going to read p.positions, p2.positions, and then p.accelerations, and then p2.accelerations. And we need dt, which we're going to say is 10. Okay, so that is doing nothing, but it's also returning something for some reason. I don't know why it's returning anything. Should I just add return none to the end here? None. Nothing? Okay, let's take a look at p. So absolutely nothing changed. Now, should something have changed? What we did here is we did 1 times 2. So that's 2 minus 1 plus 1 times 1 times 1. So it should have been, we should be returning 2 in this case, but we're not returning 2. We're returning nothing. So nothing is, like, absolutely nothing is changing. This is really bugging me. So we have the temporary position. It's going to be a copy of position 1. Let me just see if something's going wrong here. So A is going to be equal to 1, 2, 3. B is going to be equal to copy of A. B of 1 is going to be equal to 10. So B is equal to this, and A is equal to that. Perfect. Okay, so we're going to say it's a copy of position 1. So then we say position 1 is going to be equal to position 1 times 2 minus position 2 plus the acceleration 1 times dt times dt. So let's just do that computation. So it's going to be p dot positions is going to be equal to p dot positions times 2 minus p2 dot positions. What are the acceleration vectors? Right now it's just all ones, so it's all ones. Then it should be plus p dot accelerations times, yeah, p dot accelerations 2, 4. So this is working. So that line is working just fine. But when I run this in the Verlet, so that line's working. Okay. So just running that in the terminal works. But running this function doesn't. Do I just have to recompile, maybe? This should be fine. Let me just not set the second positions or the acceleration. So let's comment that out there. Write this over here. We're going to comment this out as well. So this function is literally just running that one line. And now we're going to do Galilee.Verlet here, and we're going to take a look at P. Okay, we're going to run it again. Why? I don't understand. I'm going to create a function. Julia handles arrays automatically. What do you mean? Like, I mean, yeah, I don't know. I'm sorry, give me a second. So we're going to do, it handles that automatically. I mean, we just checked that with that line. So let's do F. Function F is going to be equal to, let's do A, B, B. A is going to be equal to A plus B, end. Okay, so A is going to be equal to, okay, so we have positions. So let's do F of P dot positions. Okay, P2 dot positions. What? What? How did we get 9? FP. Oh, he's not actually updating P. Ah. All right, let's try that again. Okay, fine. Now, can you do, what happens if we read in 1 and 2? Does that actually work here? Let's define a new function. G. And now let's do G 1, 2. Yeah, I thought that would break. Oh wait, why do we have GPU arrays in here? What? What? Okay, well, in that case, we got to think about this a bit more. So at least we found a way to solve it. If we work on things vector-wise, that'll be fine. But we don't want to work on things vector-wise. We want to work on things element-wise, which was a previous problem. Okay, so just for the record, just to make sure everyone's following, what had just happened was I had written a function for Verlet that worked element-wise. So it read in a bunch of points, and it output a bunch of points in that same space. But we want to work array-wise. We want to make it work on the entire array. So I'm just going to modify the function for Verlet here. So it is a dot equals, and that should solve all of our problems. So this should be dot equals there. And that should solve all those problems. And then in here, what are we going to do? We're going to do temp position. I think I just want a dot equals for all of these guys. And then this should, in principle, solve the issue. So Galilee.Verlet here, P. Run it one more time, P. Okay, it's working now. Perfect. Can I post a link to Stack Overflow? Yeah, feel free to. Let's go there. So let's go ahead and try running this one more time. So we're going to remove, check. We don't have one. So now we're going to do Galilee.Run. Should be up here somewhere. This guy. And now we're going to take a look at GNU plot, and we should be able to plot 0. Control D, back a directory, GNU plot 0. Now we're going to do it one more time with 9, and we're going to replot that guy, and hopefully, I can't tell if they've moved or not. Crap. You've used assignment. Well, yeah, it's a bit more complicated than that. So the issue was that, yeah, right, that is the issue. But the main issue was that I was trying to write it like a kernel. So we're gonna have to rewrite this tomorrow when we do this. We're gonna have to rewrite this tomorrow when we're doing it kernel abstractions. I was trying to write it in a way that would enable me to more easily just abstract this out to what we can do with kernel abstractions. But oh well. Creating copies. Yeah, I think we're okay there. Okay, so let's go here. We're gonna cd into projects, Galilee here. And let's go into vi check.dat. Oh, we got nans. Well, that's something. How do we get ints in infinite and the initial generation here? Okay, vi remove check.dat. Let's go into vi. Let me just run it one more time. Control D, Julia, using revise. There we go. Now we're going to using Galilee. Perfect. All right, let's go into vi simulate source simulate.jl. So we're writing to file at the end of every step, which means that's how we got an infinite. Somehow we royally screwed up, and I'm not sure exactly how. I guess the issue is, okay, so somehow we have accelerated a particle so fast that it went to infinity. Not entirely sure how that happened. Yeah, let's just go here. I mean, maybe the force is just incredibly high. Let's just try making this so we have, what do I call it? Source initialize, what do I call it? I called it grid extents is equal to 1. So now we're going to do simulate.jl. The Tandav, thank you so much for following, really appreciate it. And here we're just going to initialize these with like very large grid extents and see what happens. Usually in my case it's division by 0. I don't know how we would have divided by 0 though. We don't have any division. Do we? I mean, you're right. It must have been division by 0, but I don't understand where we divided by 0. We only have a single. Oh, okay. it's in the gravity. If position 1 is equal to position 2, right? Okay, that's the issue. I got you. So it's in the find acceleration. Some of the accelerations must have been infinite. So then in that case, we're gonna do gravity here is position 1, position 2, and I guess what I'll do is if position 1 not equals to position 2, we're going to return this guy. I'm kind of running out of time, so I'm just doing some really dumb hacks. Galilee.run. 1 second. Check.dat. Well, okay. Sure. So let's go into GNU plot. And let's just plot check.dat. So there are our initial positions. Now we're going to do replot on 9. Okay, so this is a very bad plot. Let me try, what is it? Line type? No, dot type, point type, PT7. Okay, so at least we see the dots now. Replot PT7. Okay, so I'm not arguing that this is good, but we have a bunch of points down here that are definitely moving. How do we do this here? There we go. So we have a bunch of points here. The purple dots are the original ones, and the green ones are the moving points. I'm not entirely certain why they're all moving to the right. I'm also not entirely certain why we don't really have a good random distribution along X and Y. Oh, I see what's happening. Wait a minute. No, I don't see what's happening. Why is this generated at 200? Why is that so... Wait, what? A here. All of these guys should initialize between... Oh, they're so close together. Okay, wait. Let me try this one more time. I think I see what's happening here. Let's go check.dat. G down here. Set and quit. Remove check.dat. I'm sorry, guys. I'm all over the place. But I do need to go like super quick. So I'm sorry if I've been like missing comments and being like, you know, kind of like I got to go like in like 5 minutes. So let me very quickly go into the README and just go down here and just say just small things to update. Notes, I suppose, is what I'm going to do here. And so number 1, go in 1 minute. Yeah, I got to go. I'm so sorry. I'm really, really sorry. I've been missing comments and everything. So one thing I need to say here is that we work on initialization to ensure that particle acceleration is actually correct. Okay, the next one I need to say is, so I think what's happening is the particles are so close together that when you do 1 over r squared, when they're so close together, they're like literally like all right next to 1. They just go super far out, so they're flying out because of that. So I think that's what's happening. So that's what I want to check there. So next, make a more realistic gravitational force. Sure. And then after that, I think we just hop right into kernel abstractions, ... All right, just adding that in, just so I have them ready to go for next time. I think I can raid somebody if I just raid and run. Might, because we do have to raid and run. What do you guys reckon? We could do Tim, we could do Kitboga. Let me know. If you guys have someone that you want to raid, let me know. Let me go and do get status, get add. I think I can just do get add dot, get status again. No, that didn't work. Get, how do I unstage? Isn't it get reset? All right, so get add readme. I should add these to the get ignore. vi.get ignore. And I'm looking for the anything.dat and then manifest.toml. So let's go to manifest.toml and then star.dat. Get status, get add dot, get commit -m, fixing bug, and Verlay integration. All right, git push Origin, development. All right, perfect. Whew, okay. So, long story short, we've been streaming for about 4 hours today. We started today with one goal in mind, and that was getting an N-Body simulator working. We have an N-Body simulator working. It's rough. It's not exactly perfect, but it is working. Tomorrow, we'll kind of make it a bit nicer, and we'll try to implement something in parallel via kernel abstractions, and then we'll slowly but surely start adding awk trees, Barnes hut algorithms, making this as efficient as possible, working on benchmarking, tests, all that kind of stuff, and then slowly but surely adding in some new research that people have not seen before, hopefully going on to 4D galaxy simulations, all this kind of stuff, really speeding up the simulation, making it super spiffy and cool. But for today, we're done. I'm gonna go ahead and raid Kitboga because I gotta go. So like I'm gonna raid somebody and then leave. And so I don't want to like talk to them and be like, oh yeah, stream was great. Well, I don't have time for that. So I'm just gonna raid. We're gonna run out. Thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And hopefully I'll see you next time for the next episode of Simuleos when we get more done. I'm pretty excited with what we did today. And I'm hoping that we can get even more done tomorrow. Thanks again, guys, and I'll see you next time. Bye, guys.